Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient birth of our galaxy, the Milky Way. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 13.6 billion years ago, in the cooling aftermath of the universe's first light, something quiet begins. The cosmos has been expanding for several 100,000 years since the moment when photons first travelled freely through space, leaving behind the warm glow that modern telescopes detect as the cosmic microwave background. In this cooling darkness, gravity whispers to itself across vast emptiness, drawing together wisps of primordial hydrogen and helium that drift like breath in the cosmic dark. No stars yet exist. No elements heavier than lithium have been forged in the brief nuclear synthesis of the Big Bang's first minutes. Only the patient mathematics of attraction, pulling matter into loose congregations that will, over millions of centuries, become the scaffolding of galaxies. The early universe holds a temperature just warm enough for atoms to remain intact, just cool enough for gravity to overcome the outward pressure of radiation. At roughly 3000 Kelvin, hydrogen and helium atoms maintain their electronic shells, while the expanding space between them allows gravitational attraction to begin its slow work. In this delicate balance, the first dark matter halos begin their construction, invisible architects sketching the foundations of what will become the Milky Way. These phantom structures, comprising most of the mass that will ever exist in our galaxy, remain completely undetectable except for their gravitational influence, like shadows cast by invisible objects moving through dimensions we cannot perceive. The process unfolds with geological patience that makes mountain building seem hasty. Hydrogen clouds, each containing millions of solar masses worth of primordial gas, drift toward gravitational wells carved by dark matter concentrations. As they fall inward, the gas heats and compresses according to the ideal gas law, but not yet enough to ignite nuclear fusion. The temperature rises from near absolute zero toward perhaps a few hundred Kelvin, still far short of the 15 million degrees required for hydrogen nuclei to overcome their electrical repulsion and fuse into helium. For tens of millions of years, these proto-galactic clouds simply breathe, contracting under gravity, expanding under pressure, contracting again in cycles that span geological ages. The universe has learned to exhale slowly, each breath lasting longer than the entire history of complex life on Earth. During these cosmic respirations, turbulence develops within the gas clouds. Shockwaves from gravitational compression create density variations that will eventually seed the formation of the first stellar clusters. Yet the process remains so gradual that an observer, had one existed, would perceive only the faintest changes across millennia. Within these breathing clouds, small irregularities grow through a process astrophysicists call gravitational instability. Regions slightly denser than their surroundings accumulate more matter, becoming denser still, which allows them to attract even more material in an accelerating feedback loop. It is a process of amplification so gradual that galaxies, in their earliest phases, barely distinguish themselves from the cosmic background. The density contrast between future galactic regions and cosmic voids increases by factors of mere percents per million years. Only patience separates structure from emptiness. Only time transforms the uniform into the particular. The mathematics governing this process follow precise physical laws, yet the outcomes remain delicately sensitive to initial conditions. Quantum fluctuations in the early universe, tiny variations in density that emerge from the fundamental uncertainty principle, provide the seeds for all future structure. These fluctuations, stretched to cosmic scales by the rapid inflation of space in the universe's first fraction of a second, create the template upon which gravity will work for billions of years. The largest fluctuations will become galaxy clusters. Medium-sized ones will birth individual galaxies like the Milky Way, and the smallest will eventually form individual stars. The first stellar nurseries appear not as brilliant beacons but as subtle warmths in the cold. Gas densities increase by factors of hundreds, then thousands, as gravity continues its slow compression. In the densest regions, temperatures rise from the cosmic background temperature of a few Kelvin toward the threshold where molecular bonds can form and chemical processes can begin. Molecular hydrogen, the first molecule to exist in significant quantities, forms through reactions on the surfaces of tiny dust grains themselves, composed only of the lightest elements produced in Big Bang nucleosynthesis. Yet even now, in these preliminary stirrings, the galaxy to be remains mostly dark, mostly empty, mostly waiting. The universe at this epoch contains no sources of light except the fading afterglow of creation itself. No fusion reactions warm the interstellar medium. No stellar winds carve cavities in molecular clouds. No supernova explosions enrich the cosmos with heavy elements. The proto-Milky Way exists in a state of pure potential, like a vast musical instrument waiting for its first note to be played. Dark matter continues its invisible choreography during these early epochs. Computer simulations suggest that dark matter particles, whatever their nature, cluster into complex hierarchical structures through purely gravitational interactions. Smaller halos merge into larger ones, which merge into larger ones still, building the cosmic web that will guide the distribution of ordinary matter for the remainder of cosmic history. The dark matter halo that will eventually host the Milky Way grows through countless minor mergers, each adding mass and angular momentum to the system. Scientists still puzzle over the precise mechanisms that govern these earliest phases. How quickly did the first dark matter halos form? What determined which regions would birth galaxies and which would remain forever empty? The cosmic microwave background radiation offers clues, tiny temperature fluctuations that map the seeds of future structure with exquisite precision, but the details of galactic birth remain partly mysterious, like fossils of an event too distant to fully reconstruct. Modern telescopes can observe galaxies that formed when the universe was less than 1 billion years old, but the very earliest phases of galactic assembly remain hidden behind veils of neutral hydrogen that absorbed all optical light. The transition from smooth universe to structured cosmos happens gradually. Then suddenly, for hundreds of millions of years, the proto-Milky Way accumulates mass slowly and quietly. Then, as gas densities finally reach the thresholds required for gravitational collapse, the first generation of stars begins to form. This moment marks the end of the cosmic dark ages and the beginning of the universe's illumination, though that story waits for another telling. Only took a few 100 million years for gravity to gather the raw materials of an entire galaxy. Only required the patient accumulation of invisible matter to create the foundation for 400 billion future stars. Only needed the universe to cool just enough, expand just slowly enough, to allow structure to emerge from the primordial chaos of creation. The Milky Way begins not with drama, but with the universe learning to whisper its intentions across space and time, teaching matter how to organize itself into the spectacular spiral that will, billions of years later, cradle worlds capable of contemplating their own origins. In the vast architecture of space, something invisible shapes everything visible. Dark matter weaves through the cosmos like a phantom scaffolding, comprising 85% of all matter, yet revealing itself only through the gravitational choreography it conducts among stars and galaxies. Within the forming Milky Way, this unseen substance creates the fundamental structure upon which ordinary matter, hydrogen, and helium. The building blocks of stars will eventually arrange itself into the spiral patterns that define our galaxy's luminous beauty. The dark matter halo surrounding the proto-Milky Way extends far beyond what will become the visible galaxy, reaching outward perhaps 600,000 light-years from the galactic center. This invisible sphere contains roughly 10 times more mass than all the stars that will ever shine within it, yet its presence can only be inferred through its gravitational influence on ordinary matter. Like a vast, transparent bowl, the dark matter halo provides the gravitational well into which gas clouds fall, gaining speed and heat as they spiral inward toward the galaxy's eventual disk. Computer simulations reveal that dark matter organizes itself into intricate substructure clumps within clumps, streams and filaments that thread through space in patterns resembling neural networks or spider webs. These simulations, running on the world's most powerful supercomputers, model the gravitational interactions of billions of dark matter particles over cosmic time. They show how smaller dark matter halos merge into larger ones through a process called hierarchical structure formation, building cosmic architecture from the bottom up, like invisible cities growing in the dark. The nature of dark matter itself remains one of astronomy's deepest mysteries. Scientists know it interacts gravitationally with ordinary matter, but apparently through no other force. It neither emits nor absorbs light, hence its name. It passes through ordinary matter as if it were made of shadows, yet its gravitational signature appears throughout the observable universe. Leading candidates include exotic particles predicted by theories of physics beyond the standard model axions, sterile neutrinos, weakly interacting massive particles called WIMPs, but decades of increasingly sensitive experiments have yet to directly detect a single dark matter particle. Within the Milky Way's dark matter halo, ordinary matter begins its own gravitational dance. Hydrogen and helium gas, heated to millions of degrees as it falls into the galaxy's gravitational well, creates what astrophysicists call a hot halo, a tenuous atmosphere of ionized gas that surrounds the forming galaxy like an enormous, invisible aurora. This hot gas extends outward hundreds of thousands of light years, far beyond the stars, containing perhaps as much mass as all the stars in the galaxy combined. Yet it remains so diffuse that a cubic meter of this hot plasma contains fewer particles than the best vacuum achievable in Earth laboratories. The hot halo serves as a reservoir for future star formation. As this gas gradually cools through radiation, it condenses and falls inward, feeding the growth of the galactic disk over billions of years. The cooling process happens slowly, governed by the efficiency with which hot gas can radiate away its thermal energy. Heavier elements, when they eventually exist, will catalyze this cooling through their spectral lines. But in the early universe, with only hydrogen and helium available, the cooling proceeds at a more leisurely pace. Temperature variations within the hot halo create convection currents that stretch across hundreds of thousands of light years. These vast circulation patterns, larger than most galaxies, redistribute matter and energy throughout the galactic system, like atmospheric circulation on a planetary scale, but vastly more extended. These currents help determine where and when gas will cool and condense into the denser structures that eventually form stars. Dark matter's influence extends beyond mere gravitational scaffolding. The invisible matter provides dynamical friction that helps regulate the growth of the galaxy's central regions. As clumps of ordinary matter spiral inward through the dark matter halo, they experience a drag force that causes them to lose orbital energy and spiral closer to the galactic center. This process, called dynamical friction, operates on timescales of hundreds of millions of years, slowly concentrating mass in the galaxy's central regions and contributing to the formation of what will eventually become the galactic bulge. The dark matter halo also exhibits what scientists call cuspy density profiles, regions where the dark matter density increases sharply toward the galactic center. These mathematical descriptions, derived from cosmological simulations, predict specific relationships between a galaxy's rotation curve and its underlying dark matter distribution. Yet observations of real galaxies sometimes disagree with these predictions, suggesting that the interaction between dark matter and ordinary matter during galaxy formation may be more complex than current models assume. Subhalos of dark matter, remnants of smaller structures that merged with the proto-Milky Way billions of years ago, continue to orbit within the larger halo like ghosts of ancient cosmic collisions. These dark matter satellites, typically containing millions to billions of solar masses of invisible matter, may number in the thousands throughout the galaxy's extended halo. Some of these subhalos may have retained enough ordinary matter to form small satellite galaxies, the dwarf spheroidals, that orbit the Milky Way today, while others remain completely dark, detectable only through their gravitational effects on nearby stars. The cosmic web of dark matter filaments connects the Milky Way to neighboring galaxies across tens of millions of light years. These invisible highways, along which matter flows between galaxy clusters, continue to feed fresh gas into the galaxy's outer regions even today. The local group, containing the Milky Way, Andromeda, and dozens of smaller galaxies, sits at the intersection of several dark matter filaments that channel material from the cosmic voids toward gravitationally bound structures. Scientists probe dark matter's properties through gravitational lensing, observing how the invisible mass bends light from background galaxies like a cosmic magnifying glass. These observations reveal dark matter's distribution with increasing precision, mapping its clumpy structure and measuring its total abundance. The results consistently confirm that dark matter outweighs ordinary matter by more than 5 to 1 throughout the universe, making the luminous stars and gas clouds that we can see directly merely the visible foam on an invisible ocean. Modern experiments buried deep underground search for evidence of dark matter particles interacting with ordinary matter through forces beyond gravity. These detectors, shielded from cosmic rays by miles of rock, wait patiently for the rare collision between a dark matter particle and an atomic nucleus. Other experiments attempt to create dark matter particles in high-energy collisions at particle accelerators, while space-based telescopes search for the gamma rays that might be produced when dark matter particles annihilate each other. Only took gravity to reveal dark matter's existence through the motions of stars and galaxies. Only required careful observation to discover that most of the universe remains invisible to our instruments. Only needed the patient accumulation of evidence to realize that the cosmos we see represents merely the luminous minority in a predominantly dark universe. Dark matter shapes galactic evolution through pure gravitational influence, conducting the cosmic symphony while remaining forever silent, forever unseen, forever mysterious in its fundamental nature. At the heart of the forming Milky Way, in a region that will not acquire a proper name for billions of years, something massive and patient grows in absolute darkness. Sagittarius A star, Escarius, to astronomers accumulates mass grain by grain, gas cloud by gas cloud, through gravitational processes so inexorable that they operate like cosmic clockwork across geological time. 4 million times more massive than the Sun. This supermassive black hole represents one of the universe's most extreme objects, a region where space and time curve so severely that not even light can escape once it crosses the event horizon. The black hole's formation remains shrouded in theoretical uncertainty. Did it grow from the collapsed remnants of the first generation of massive stars, slowly accumulating mass over billions of years, or did it form more directly from the gravitational collapse of primordial gas clouds in the galaxy's earliest epochs? Computer simulations suggest multiple pathways, but the observational evidence for black hole formation in the early universe remains fragmentary, like trying to reconstruct the growth of a forest from examining only its current canopy. SGR-A sits precisely at the gravitational center of the galaxy, anchoring the orbital motions of 400 billion stars. Its gravitational influence extends outward in diminishing strength, following the inverse square law that governs all gravitational interactions. At the distance of Earth, some 26,000 light-years away, the black hole's gravitational pull contributes only a tiny fraction to the forces that bind the solar system to the galaxy, yet its presence provides the fundamental reference point around which the entire galactic structure organizes itself. The event horizon of Sussa A measures approximately 24 million kilometers across roughly the size of Mercury's orbit around the Sun. Within this boundary, the curvature of spacetime becomes so extreme that all trajectories lead inexorably inward. No information can escape from within the event horizon, making the black hole's interior forever inaccessible to external observation. Einstein's general relativity predicts that time dilation near the event horizon stretches moments into eternities as seen from the outside, creating a temporal gradient that borders on the philosophical. Around the black hole, matter organizes itself into an accretion disk, a swirling maelstrom of gas and dust heated to millions of degrees by gravitational compression and friction. This disk exhibits complex magneto-hydrodynamic behavior, with magnetic field lines threading through the plasma and launching jets of particles at nearly the speed of light along the black hole's rotation axis. These relativistic jets, though currently quiescent in SGR, demonstrate the black hole's capacity to influence matter across vast distances when supplied with sufficient fuel. The accretion process operates with mechanical precision, governed by conservation of angular momentum. As matter spirals inward, it must shed angular momentum to continue its descent toward the event horizon. This angular momentum transfer heats the infalling material through viscous dissipation, causing it to radiate energy across the electromagnetic spectrum. The efficiency of this process, converting rest mass directly into radiant energy, exceeds that of nuclear fusion by factors of 10 or more, making accretion onto black holes one of the most efficient energy sources in the universe. Periodically, SGR-A experiences what astronomers call flaring events, sudden increases in its luminosity that occur on timescales of hours or days. These flares likely result from temporary increases in the accretion rate, perhaps triggered when clumps of matter or entire stars venture too close to the event horizon. During these episodes, the black hole's luminosity can increase by factors of hundreds, briefly outshining the combined light of thousands of normal stars before fading back to quiescence. The space immediately surrounding Escar A contains some of the most extreme stellar orbits in the galaxy. Stars designated S2, S62, and others follow highly elliptical paths that bring them within hundreds of astronomical units of the black hole closer than Pluto orbits the Sun. These stars experience gravitational accelerations thousands of times stronger than anything found in the outer galaxy. Reaching speeds of several % of light speed at closest approach, their orbital periods, measured in decades rather than millions of years, provide laboratories for testing Einstein's general relativity under conditions impossible to replicate on Earth. Observations of these close-orbiting stars have confirmed several predictions of general relativity with unprecedented precision. The precession of their elliptical orbits, caused by the curvature of spacetime near the black hole, matches Einstein's calculations to within observational uncertainty. The gravitational redshift of starlight climbing out of the black hole's gravitational well has been measured directly, showing how time itself runs slower in regions of strong gravitational field. The black hole's rotation, its spin-angular momentum, adds additional complexity to the spacetime geometry in its vicinity. Current measurements suggest that SCREE rotates at a significant fraction of its theoretical maximum, dragging spacetime itself around in a phenomenon called frame dragging, or the lens-Thirring effect. This rotation creates ergospheres and other exotic spacetime features that exist nowhere else in the local universe, making the galactic center a natural laboratory for gravitational physics. Surrounding the immediate vicinity of Escar A then lies a dense stellar cluster, containing millions of stars packed into a region only a few light-years across. This nuclear star cluster represents one of the densest stellar environments in the galaxy, where close encounters between stars occur millions of times more frequently than in the solar neighborhood. Many of these stars show peculiar properties enhanced helium abundances, unusual chemical compositions that suggest they formed under the extreme conditions prevailing near the galactic center. The formation and evolution of this central stellar cluster remains an active area of research. Did these stars form in place, condensing from gas clouds that somehow avoided being disrupted by the black hole's tidal forces? Or did they migrate inward from larger galactic radii through gravitational interactions and dynamical friction? Observations reveal ongoing star formation even in this hostile environment, with massive young stars somehow managing to assemble despite the black hole's disruptive influence. Tidal forces near Escar A stretch objects along the radial direction while compressing them tangentially, an effect that becomes catastrophic for extended objects venturing too close to the event horizon. The tidal radius, the distance at which tidal forces overcome an object's self-gravity, lies well outside the event horizon for most astronomical bodies. Stars that cross this boundary experience spaghettification, being stretched into long, thin streams of matter that eventually spiral into the black hole. The black hole occasionally captures and disrupts entire stars through these tidal interactions, events that produce dramatic flares observable across the electromagnetic spectrum. These tidal disruption events occur perhaps once every 10,000 years in a typical galaxy, creating sudden increases in the black hole's accretion rate and luminosity that can be seen from billions of light-years away. The debris from disrupted stars feeds the black hole for months or years, creating extended periods of enhanced activity. Only took 4 million solar masses concentrated into a region smaller than our solar system to anchor an entire galaxy. Only required the patient accumulation of matter over cosmic time to create gravitational fields so strong they bend light itself. Only needed the universe to permit such extreme concentrations of mass and energy to demonstrate that reality surpasses imagination in its capacity for the extraordinary. Sagittarius A star spins silently at the galaxy's heart, patient and inexorable, a cosmic lighthouse whose beacon points inward toward mysteries that may forever remain beyond direct observation. In the primordial darkness of the early Milky Way, a generation of stellar giants awakens to brief, brilliant lives. Population 3 stars, the first stars ever to shine in the universe, ignite from clouds of pure hydrogen and helium, unmarked by heavier elements because no heavier elements yet exist. These massive suns burn with nuclear fires that will forge the chemical foundations of all future complexity, their cores becoming cosmic furnaces where the periodic table begins its slow construction element by element. The first stars form when primordial gas clouds finally collapse under their own gravity, after hundreds of millions of years of gradual accumulation. Without dust grains or heavy elements to facilitate cooling, these early clouds must rely on molecular hydrogen to radiate away their thermal energy. This inefficient cooling process means that only the most massive gas concentrations can collapse completely, leading to the formation of stars with masses perhaps 50 to several hundred times greater than the Sun. These stellar behemoths live fast and die young, their nuclear fuel consumed in mere millions of years rather than the billions required for smaller stars. Population 3 stars shine with luminosities thousands of times greater than the Sun, their surfaces heated to temperatures exceeding 50,000 Kelvin by the furious nuclear reactions in their cores. This makes them appear intensely blue-white, though no eyes exist to witness their light in the early universe. Their stellar winds, accelerated by radiation pressure, carry matter away from their surfaces at speeds of thousands of kilometers per second, carving the first cavities in the pristine interstellar medium and beginning the process of chemical enrichment that will eventually make planets and life possible. Deep within their cores, these massive stars perform nuclear alchemy on an unprecedented scale. Hydrogen fuses into helium through the proton-proton chain and CNO cycle, but since no carbon, nitrogen, or oxygen yet exists, the CNO cycle cannot operate in the first generation. The stars must rely entirely on the slower proton-proton process, though their enormous masses still drive core temperatures high enough to sustain rapid fusion. As hydrogen depletes in their cores, they begin burning helium into carbon and oxygen, then carbon into neon and magnesium, continuing up the periodic table through silicon burning until their cores fill with iron peak elements. The progression from hydrogen to iron follows a precise sequence governed by nuclear physics and stellar structure. Each successive fusion stage requires higher temperatures and occurs more rapidly than the last. Hydrogen burning might sustain a population 3 star for several million years, helium burning for hundreds of thousands of years, carbon burning for thousands of years, and silicon burning for mere days. The final stages of nuclear evolution occur so rapidly that stellar structure cannot adjust to the changing energy output, leading to increasingly unstable conditions in the stellar core. Iron represents the end of energy-producing fusion reactions. Elements lighter than iron release energy when fused together, while elements heavier than iron require energy input to create them. When the core of a population 3 star fills with iron peak elements, iron, nickel, cobalt nuclear energy generation ceases entirely. The core, no longer supported by radiation pressure from fusion reactions, begins to collapse under its own immense gravitational pull. What happens next unfolds on timescales measured in seconds rather than years, a catastrophic implosion that marks the star's transformation from creator to destroyer. The core collapse proceeds with devastating efficiency. In less than a second, a region the size of Earth compresses to a sphere only 20 kilometers across, reaching nuclear densities where protons and electrons merge to form neutrons. The collapse halts abruptly when the core reaches these nuclear densities, creating a shock wave that propagates outward through the star's envelope at speeds of 30,000 kilometers per second. This shock wave, initially driven by the core bounce, stalls as it encounters the star's outer layers, but receives renewed energy from neutrino heating and other complex processes that remain incompletely understood. The resulting explosion, a core collapse supernova, releases more energy in seconds than the star produced during its entire main sequence lifetime. The explosion's luminosity can briefly equal that of an entire galaxy, making single population 3 supernovae visible across cosmological distances. These explosions inject the first heavy elements into the pristine interstellar medium, seeding space with carbon, oxygen, silicon, iron, and dozens of other elements essential for the formation of rocky planets and biological chemistry. Beyond iron, the supernova's extreme conditions enable the creation of elements that cannot form through normal stellar nuclear synthesis. Rapid neutron capture during the explosion's first few seconds creates neutron-rich isotopes that decay into elements heavier than iron. Gold, platinum, uranium, and other heavy elements owe their existence to these violent moments when neutron densities exceed those found in atomic nuclei. The R process, as astronomers call this rapid neutron capture, operates only in the most extreme environments, supernovae, neutron star mergers, and other catastrophic events. The supernova shockwave travels outward for thousands of years, sweeping up surrounding gas and dust to create an expanding bubble of hot plasma hundreds of light years across. These supernova remnants inject enormous quantities of energy into the interstellar medium, driving turbulence and triggering new episodes of star formation in nearby molecular clouds. The mechanical energy from population 3 supernovae may have been sufficient to blow gas entirely out of the small dark matter halos where the first stars formed, preventing further star formation in these mini-halos and forcing subsequent stellar birth to occur in more massive systems. Some population 3 stars may have been so massive that they bypassed the supernova stage entirely, collapsing directly into black holes without explosive ejection of their outer layers. These hypothetical objects, with masses exceeding perhaps 250 times the Sun's mass, would have consumed themselves completely, leaving behind intermediate mass black holes as their sole legacy. Such black holes might serve as seeds for the supermassive black holes found at galaxy centers today, though direct observational evidence for this formation channel remains elusive. The chemical signatures of population 3 nucleosynthesis appear in the most metal-poor stars observable today. These ancient stars, born from gas clouds enriched by only one or a few population 3 supernovae, preserve fossil records of the first stellar explosions in their atmospheric compositions. By analyzing the abundances of various elements in these stellar atmospheres, astronomers can reconstruct the masses and explosion energies of the population 3 stars that enrich their birth clouds. Current theoretical models predict that population 3 stars should have formed with a characteristic mass scale around 100 solar masses, though the actual mass distribution remains uncertain. The lack of heavy elements in primordial gas clouds affects both the cooling efficiency during collapse and the opacity of the resulting stellar atmospheres, making population 3 stars fundamentally different from any generation of stars that followed. Their brief lives and violent deaths mark the end of the universe's age of innocence and the beginning of chemical evolution that continues today. The transition from population 3 to population 2 star formation occurred gradually as heavy element abundances increased throughout the early universe. Once the metallicity of gas clouds reached approximately 1,000th of solar abundance, dust grains could form and enhance cooling efficiency, allowing smaller stars to form alongside the massive ones. This transition, occurring perhaps 1 billion years after the Big Bang, marked the beginning of stellar populations capable of burning for billions of years rather than mere millions. Only took a few million years for the first stars to transform the chemical composition of the entire universe. Only required the nuclear fires of massive stellar cores to forge the elements essential for planets and life. Only needed the violent deaths of stellar giants to seed space with the raw materials for complexity. Population 3 stars live and die in cosmic adolescence, their brief existence bridging the gap between the universe's primordial simplicity and the chemical richness that surrounds us today. Their legacy written in every carbon atom, every oxygen molecule, every grain of cosmic dust. Across millions of years, the infant Milky Way learns the elegant mathematics of rotation. Gas clouds, initially falling toward the galactic center in chaotic trajectories, gradually settle into a thin, rotating disk through the inexorable operation of angular momentum conservation. Like a figure skater drawing in her arms, the collapsing gas spins faster as it contracts, but unlike the skater, the galaxy's rotation creates a centrifugal force that eventually balances gravity's inward pull, establishing a stable, flattened structure that will define the galaxy's appearance for billions of years to come. The process begins with the fundamental physics of colliding gas clouds. As hydrogen and helium streams fall into the galaxy's gravitational well from different directions, they carry with them the rotational motion inherited from the primordial fluctuations that seeded galaxy formation. These gas streams possess slight net angular momentum, a statistical inevitability when matter accretes from multiple directions around a gravitational center. The total angular momentum of all infalling material, while small compared to the galaxy's eventual rotational energy, provides the seed that will grow into the magnificent spiral structure visible today. Angular momentum conservation operates with mathematical precision throughout the galactic collapse. Each parcel of gas carries angular momentum proportional to its mass, velocity, and distance from the rotation axis. As gravity pulls this gas inward, conservation laws require that the rotational velocity increase to compensate for the decreasing radius. This creates a natural tendency for infalling material to speed up tangentially as it approaches the galactic center, gradually transforming radial infall into circular orbital motion. The formation of the galactic disk occurs through a process astronomers call dissipational collapse. Unlike dark matter, which interacts only gravitationally and retains its three-dimensional distribution in the galactic halo, ordinary matter can lose energy through radiation and physical collisions between gas particles. This energy loss allows gas clouds to settle into the gravitational potential well more completely, spiraling inward until centrifugal force balances gravity in the plane of rotation. The result is a dramatic flattening of the gas distribution from a roughly spherical halo into a thin disk only a few thousand light-years thick, but 100,000 light-years across. Collisions between gas clouds during this settling process generate shock waves that heat the gas temporarily, but ultimately remove energy from the system through radiative cooling. Hot gas radiates energy away in the form of photons, allowing the material to lose the random thermal motion that would otherwise support it against gravitational collapse. This cooling process operates most efficiently at intermediate densities and temperatures, creating a natural timescale for disk formation measured in hundreds of millions of years. The disk's final thickness results from a delicate balance between gravitational compression and pressure support from random gas motions. Gravity attempts to collapse the gas into an infinitely thin plane, but thermal pressure from residual gas heating, turbulence from ongoing accretion, and stellar winds from newly formed stars all contribute to maintaining a finite disk thickness. The equilibrium thickness depends on the gas temperature, the local gravitational field strength, and the efficiency of energy dissipation mechanisms. As the gas settles into the disk, it develops a characteristic rotation curve that reflects the galaxy's underlying mass distribution. In the inner regions, where most of the galaxy's mass concentrates near the center, orbital velocities increase with radius according to Keplerian dynamics, similar to planetary motion around the Sun. However, in the outer regions, the distributed mass of the dark matter halo creates a nearly flat rotation curve, where orbital velocities remain approximately constant with increasing radius. This transition from Keplerian to flat rotation occurs at the characteristic scale length of the galaxy's exponential disk profile. The exponential disk structure emerges naturally from the physics of angular momentum conservation and energy dissipation. Gas with higher angular momentum settles at larger radii, while lower angular momentum material spirals closer to the galactic center. The resulting surface density profile follows an exponential decline with radius, a mathematical relationship observed in disk galaxies throughout the universe. This exponential law reflects the statistical distribution of angular momentum in the original gas supply and the efficiency of angular momentum transport during disk formation. Turbulence plays a crucial role in establishing the disk's final structure. Random motions generated by gravitational instabilities, supernova explosions, and stellar winds create a three-dimensional velocity field that redistributes both matter and angular momentum throughout the forming disk. This turbulence prevents the gas from settling into perfectly circular orbits, instead creating a thick disk component with higher velocity dispersion than the eventual thin disk that forms as the turbulence gradually decays. The disk formation process creates natural sites for enhanced star formation along spiral density waves that develop from gravitational instabilities in the rotating gas. These density waves propagate through the disk like ripples on a pond, compressing gas clouds and triggering episodes of stellar birth that will eventually create the galaxy's distinctive spiral arm structure. The feedback from newly formed stars' stellar winds, radiation pressure, supernova explosions helps regulate the star formation rate and prevents the disk from converting all its gas into stars too rapidly. Magnetic fields thread through the forming disk, carried inward with the accreting gas and amplified by the disk's differential rotation. These magnetic fields provide additional pressure support against gravitational collapse and couple to the ionized fraction of the gas, creating magnetohydrodynamic waves that transport angular momentum outward while allowing matter to spiral inward. The resulting magnetorotational instability drives turbulence that enhances the accretion rate and helps establish the disk's final configuration. Chemical gradients develop naturally during disk formation as the metallicity of accreting gas varies with time and location. The innermost regions of the disk, where gas accumulates first and star formation begins earliest, become enriched with heavy elements more rapidly than the outer regions. This creates a metallicity gradient that decreases with galactic radius, a pattern observed in spiral galaxies today and preserved as a fossil record of the disk formation epoch. The timescale for disk formation depends on the efficiency of angular momentum transport and energy dissipation mechanisms. Computer simulations suggest that the basic disk structure establishes itself within the first few billion years of the galaxy's existence. Though gas accretion and disk growth continue at diminishing rates throughout cosmic time, the early universe's higher gas densities and more frequent galaxy interactions may have accelerated disk formation, compared to processes operating in the present epoch. Warps and asymmetries in the forming disk result from the ongoing accretion of gas with misaligned angular momentum vectors. Perfect axis symmetry would require all accreting material to possess identical angular momentum directions, a statistical impossibility given the chaotic nature of early structure formation. These departures from perfect symmetry seed the development of spiral arms, bars, and other non-axis symmetric features that will characterize the galaxy's mature structure. The gravitational influence of nearby forming galaxies affects disk formation through tidal torques that can either enhance or suppress the angular momentum of accreting gas. The proto-Milky Way's interactions with what will become the Andromeda Galaxy, the large and small Magellanic Clouds, and other members of the local group all contribute to the final orientation and rotation properties of the galactic disk. Only took conservation of angular momentum to transform chaotic gas infill into orderly rotation. Only required the patient operation of energy dissipation to flatten three-dimensional chaos into two-dimensional elegance. Only needed the interplay between gravity and centrifugal force to establish the stable configuration that will house 400 billion stars. The Milky Way's disk forms through the universe, learning to spin, transforming the random motions of primordial gas into the stately rotation that will persist for cosmic ages. A celestial dance that turns disorder into the structured beauty of spiral arms reaching across space. Through the settled disk of the Milky Way, phantom patterns begin their eternal march. Spiral arms sweep through stellar populations like slow-motion waves, taking tens of millions of years to complete a single circuit around the galactic center. Yet these magnificent structures, so prominent in photographs of spiral galaxies, exist not as permanent features but as transient density enhancements, traffic jams in the flow of stars and gas that persist while their constituent material continuously enters and exits the pattern. The spiral arms represent one of astronomy's most elegant illusions, seemingly solid structures that are, in fact, ephemeral disturbances propagating through an ever-changing medium. The spiral pattern emerges from gravitational instabilities that develop naturally in rotating disk galaxies. Computer simulations reveal that perfectly smooth, axisymmetric disks remain unstable to small perturbations, particularly those with wavelengths comparable to the galaxy's characteristic scale length. These perturbations grow exponentially through a process called swing amplification, where the galaxy's differential rotation, the tendency for inner regions to orbit faster than outer regions, stretches radial disturbances into trailing spiral shapes that wrap around the galactic center like cream stirred into coffee. Lin and Shu's density wave theory, formulated in the 1960s, provides the mathematical framework for understanding spiral structure as a propagating wave phenomenon. According to this theory, spiral arms represent regions where the gravitational potential exhibits periodic variations that compress passing material without permanently capturing it. Stars and gas clouds orbit the galaxy at their natural frequencies determined by the local gravitational field, but they experience additional acceleration as they pass through the spiral density waves, creating temporary traffic jams where material accumulates before continuing on its orbital path. The spiral wave pattern rotates at its own characteristic frequency, called the pattern speed, which differs from the orbital frequencies of individual stars and gas clouds. This difference creates what astronomers term resonances locations, where the orbital frequency of disk material matches some simple fraction of the pattern speed. The corrotation resonance, where material orbits at exactly the pattern speed, marks the outer boundary of the spiral pattern. Inside this radius, stars orbit faster than the pattern and catch up to spiral arms from behind, While outside this radius, stars orbit more slowly and are overtaken by the approaching pattern. At the inner Lindblad resonance, where stars complete exactly 2 orbits for every 1 rotation of the spiral pattern, the gravitational effects become particularly complex. Material at this resonance experiences periodic gravitational kicks that can either enhance or suppress spiral wave propagation, depending on the detailed dynamics. This resonance often coincides with the formation of bars elongated stellar distributions that develop in the central regions of many spiral galaxies, including the Milky Way. The spiral arms serve as stellar nurseries where new generations of stars form at enhanced rates. The density waves compress molecular gas clouds as they sweep through the galactic disk, triggering gravitational collapse and stellar birth. Massive, short-lived stars that form in these compressed regions illuminate the spiral arms with brilliant blue light, making the arms appear as prominent features in galaxy photographs. However, these massive stars burn out and die before they can orbit far from their birthplaces, creating the illusion that the spiral arms themselves are luminous structures. Lower mass stars, which burn for billions of years, distribute themselves more uniformly throughout the galactic disk as they complete multiple orbits during their lifetimes. These longer-lived stars, along with older stellar populations, contribute to the galaxy's overall luminosity, but do not preferentially trace the spiral pattern. This age-dependent distribution explains why spiral arms appear most prominent in ultraviolet and blue light emitted by young, massive stars, while appearing much less distinct in infrared light dominated by older stellar populations. The morphology of spiral arms, their pitch angle, number, and degree of winding depends on the balance between the restoring force of gravity and the dispersive effects of differential rotation. Tightly wound spirals with small pitch angles develop in systems where gravity dominates, while more open spirals form when differential rotation more effectively disperses density enhancements. The Milky Way exhibits a moderately open 2-armed spiral pattern with a pitch angle of approximately 12 degrees, suggesting an intermediate balance between these competing effects. Magnetic fields threading through the galactic disk interact with the spiral density waves, creating magneto-hydrodynamic effects that can both enhance and complicate the wave propagation. The interstellar magnetic field, aligned partially with the spiral arms, provides additional pressure support against gravitational compression while also facilitating the formation of molecular clouds through magnetic flux compression. These magnetic effects contribute to the observed correlation between spiral arms and enhanced star formation rates. Stellar feedback processes, supernovae, stellar winds, and radiation pressure from newly formed massive stars inject energy and momentum into the interstellar medium, creating bubbles and cavities that can disrupt spiral wave propagation. This feedback operates on timescales much shorter than the spiral wave period, creating a complex interplay between star formation, stellar evolution, and large-scale galactic dynamics. The resulting turbulence helps maintain the galaxy's thick disk component and may contribute to the observed asymmetries in spiral arm structure. The persistence of spiral patterns over cosmological timescales presents theoretical challenges known as the winding problem. If spiral arms were simply material structures rotating with the disk, differential rotation would wrap them into tight spirals within a few 100 million years, far shorter than the galaxy's age. The density wave theory resolves this paradox by treating spiral arms as wave phenomena that maintain their shape while individual particles flow through them, similar to how ocean waves preserve their form while water molecules follow circular orbits. Gravitational interactions with satellite galaxies can trigger or modify spiral wave patterns through tidal forces that create asymmetric perturbations in the galactic disk. The Large and Small Magellanic Clouds, orbiting the Milky Way at distances of roughly 50 and 60,000 light-years respectively, exert tidal forces that may contribute to the galaxy's observed spiral structure and the warping of its outer disk. These interactions demonstrate how spiral patterns can respond dynamically to external gravitational influences. Modern observations reveal that real spiral galaxies exhibit far more complexity than idealized density wave models predict. Multiple spiral modes can coexist and interact, creating time-variable patterns that evolve over hundreds of millions of years. Some galaxies show grand design spirals with well-defined 2-armed patterns, while others exhibit flocculent spirals with multiple types of fragmented arm segments. The Milky Way appears to fall into an intermediate category, with a basic two-armed pattern supplemented by numerous spurs and branching structures. N-body simulations incorporating gas dynamics, star formation, and stellar feedback reveal that spiral patterns can be transient phenomena, appearing and disappearing over galactic evolutionary timescales. These simulations suggest that spiral arms may be recurrent features that periodically develop, persist for several 100 million years, then fade away before reforming in slightly different configurations. This temporal variability challenges the notion of spiral arms as permanent galactic structures. The spiral arms also serve as highways for radial migration of stars and gas within the galactic disk. Gravitational interactions with spiral density waves can change the orbital angular momentum of disk material, causing stars to migrate inward or outward over their lifetimes. This migration process redistributes chemical elements throughout the disk and may explain some of the observed scatter in metallicity gradients and stellar age abundance relationships. Recent observations of external galaxies reveal that spiral patterns often extend well beyond the visible stellar disk into the realm of neutral hydrogen gas. These extended spiral structures, visible in radio observations of the 21-centimeter hydrogen line, demonstrate that density wave patterns can propagate through regions where stellar densities are too low to maintain the gravitational amplification mechanisms that operate in the inner disk. Only took gravitational instability to create patterns that outlast their constituent material. Only required differential rotation to transform radial perturbations into trailing spiral waves. Only needed the patient propagation of density disturbances to sculpt the galaxy's most recognizable features. Spiral arms march through the Milky Way like ghostly formations, gathering stars and gas into temporary concentrations before releasing them to continue their individual orbital journeys, teaching the galaxy how to maintain structure while embracing perpetual change. Beauty emerging from the mathematical inevitability of wave physics operating on cosmic scales. In the vast spherical halo surrounding the Milky Way's disk, ancient stellar cities drift through three-dimensional space like cosmic lighthouses scattered across an ocean of darkness. Globular clusters gravitationally bound collections of hundreds of thousands to millions of stars orbit the galaxy in elongated ellipses that carry them from the outer halo to within a few thousand light-years of the galactic center, and back again over periods of hundreds of millions of years. These stellar fossils preserve the conditions that existed when the galaxy was young, their ages approaching that of the universe itself, their chemical compositions recording the earliest epochs of stellar nucleosynthesis. The Milky Way hosts approximately 150 known globular clusters, though the total population may exceed 200 when accounting for clusters hidden behind dust clouds or disrupted by tidal forces over cosmic time. Each cluster represents a single stellar generation born from the same molecular cloud, creating populations with remarkably uniform ages and chemical compositions within each cluster. This uniformity contrasts sharply with the complex stellar populations found in the galactic disk, where star formation has proceeded continuously for billions of years. Globular clusters exhibit a distinctive spatial distribution that reflects the galaxy's early formation history. Most clusters reside in a roughly spherical halo, extending perhaps 300,000 light-years from the galactic center, following highly eccentric orbits with random orientations that show little correlation with the galaxy's current rotation. This spatial arrangement suggests that globular clusters formed before the galaxy settled into its present disk configuration, when the proto-Milky Way existed as a more chaotic, three-dimensional system undergoing violent gravitational collapse. The stars within globular clusters pack together at densities thousands of times greater than found in the solar neighborhood. In the dense cores of the most massive clusters, individual stars may pass within a few astronomical units of each other, close enough for significant gravitational interactions that can alter stellar orbits and occasionally eject stars from the cluster entirely. These dynamical processes operate over timescales of billions of years, gradually evaporating the outermost cluster members while concentrating mass toward the center through a process analogous to gravitational thermalization. Two distinct populations of globular clusters orbit the Milky Way, distinguished by their metallicities, spatial distributions, and kinematics. The metal-poor population, with heavy element abundances only a few % of solar values, occupies a roughly spherical distribution extending to large galactocentric distances. These clusters likely formed during the galaxy's initial collapse phase, when the interstellar medium remained relatively unpolluted by supernova ejecta from previous stellar generations. The metal-rich globular cluster population exhibits a more flattened distribution that correlates with the galactic disk and bulge, suggesting formation during later epochs when the galaxy had already established its current structure. These clusters show heavy element abundances approaching 10 to 20% of solar values, indicating formation from gas that had been enriched by multiple generations of stellar nucleosynthesis. The dichotomy between metal-poor and metal-rich globular cluster populations provides evidence for multiple episodes of cluster formation during the galaxy's assembly. Within individual globular clusters, subtle chemical abundance patterns reveal the complex nucleosynthetic processes operating in their stellar populations. Many clusters exhibit anticorrelations between carbon and nitrogen abundances, as well as between oxygen and sodium, suggesting that cluster stars have been polluted by material processed through hydrogen burning at high temperatures. These abundance patterns indicate that globular clusters experience self-enrichment events early in their histories, possibly from winds expelled by asymptotic giant branch stars or from the ejecta of massive stellar collisions. The horizontal branch morphology of globular clusters, the distribution of evolved stars burning helium in their cores, varies systematically with metallicity, age, and possibly helium abundance. This morphological diversity suggests that globular clusters may not be as simple or uniform as once believed, with some clusters potentially hosting multiple stellar generations with slightly different chemical compositions. The presence of multiple stellar populations within individual clusters challenges traditional models of globular cluster formation and evolution. Tidal forces from the galaxy's gravitational field continuously reshape globular cluster structures over cosmic time. Clusters following eccentric orbits experience varying tidal stresses as they move between apocenter and pericenter, with the strongest forces occurring during close passages through the galactic center or disk plane. These tidal encounters strip away the outermost cluster members, creating leading and trailing tidal tails that can extend for hundreds of parsecs along the cluster's orbital path. Some globular clusters have been completely disrupted by tidal forces, leaving behind stellar streams that trace their former orbital paths through the galactic halo. These tidal streams provide powerful probes of the galaxy's gravitational potential, as the precise morphology of the streams depends sensitively on the distribution of dark matter within the galactic halo. Observations of stream properties allow astronomers to map the halo's mass distribution and test models of dark matter structure on galactic scales. The most massive globular clusters may harbour intermediate mass black holes in their centres, objects with masses between stellar mass black holes and the supermassive black holes found in galaxy nuclei. These hypothetical objects would form through the collapse of very massive stars in the cluster's early history, or through the progressive merger of stellar mass black holes that sink to the cluster centre through dynamical friction. However, observational evidence for intermediate mass black holes in globular clusters remains inconclusive, with alternative explanations possible for most claimed detections. Globular cluster ages, determined through comparison of their colour magnitude diagrams with stellar evolution models, provide crucial constraints on the age of the universe and the formation timescales of galaxies. The oldest globular clusters appear to have formed within 1 billion years of the Big Bang, making them among the most ancient objects in the local universe. These age measurements played a historically important role in establishing the cosmic age scale and demonstrating that globular clusters formed very early in cosmic history. The kinematics of globular clusters, their space velocities and orbital properties, preserve information about the galaxy's assembly history and the accretion of smaller systems over cosmic time. Clusters associated with disrupted satellite galaxies often share similar orbital characteristics, moving in coherent streams that can be traced back to specific accretion events. The Sagittarius dwarf galaxy, currently being torn apart by the Milky Way's tidal forces, has contributed several globular clusters that now orbit within the galaxy's halo. Modern surveys have discovered numerous new globular clusters in the outer regions of the galactic halo, some at distances exceeding 100,000 light-years from the galactic center. These distant clusters may represent the surviving remnants of satellite galaxies that merged with the Milky Way billions of years ago, their host galaxies having been completely disrupted while the more tightly bound globular clusters survived the tidal encounter. The stellar initial mass function within globular clusters appears to differ from that observed in present-day star-forming regions. with some clusters showing evidence for top-heavy initial mass functions that produced unusually large numbers of massive stars. This difference may reflect the extreme conditions prevailing during globular cluster formation in the early universe, when gas densities, temperatures, and turbulence levels differed significantly from those found in contemporary molecular clouds. Globular clusters serve as laboratories for studying stellar evolution under conditions impossible to replicate elsewhere in the galaxy. The combination of high stellar densities, uniform ages, and low metallicities creates environments where exotic stellar interactions, blue stragglers, X-ray binaries, millisecond pulsars occur with enhanced frequency. These objects provide insights into stellar evolution processes that operate on timescales comparable to the age of the universe. The total mass budget of globular clusters within the Milky Way amounts to only a small fraction of the galaxy's stellar mass, yet their formation likely consumed a significant fraction of the available gas during the galaxy's early epochs. This apparent inefficiency in globular cluster formation suggests that most protocluster gas clouds were disrupted by supernova feedback or tidal forces before they could convert their entire mass into stars, leaving behind only the most gravitationally bound cores as surviving globular clusters. Only took the galaxy's earliest epochs to create stellar systems that would survive for cosmic ages, only required the most extreme star-forming conditions to forge clusters dense enough to resist billions of years of tidal disruption, only needed gravity's patient work to preserve fossils of the universe's youth in stellar arrangements that continue their ancient orbits, carrying messages from the Milky Way's childhood written in the light of ancient suns, their journeys through three-dimensional space marking time with the stately precision of cosmic clockwork. Through billions of years of stellar births and deaths, the Milky Way slowly transforms its chemical composition from primordial simplicity toward the complex abundance patterns that surround us today. Metallicity, the astronomical term for all elements heavier than hydrogen and helium, increases gradually throughout the galaxy, as successive generations of stars forge heavy elements in their nuclear cores and disperse them through space via stellar winds and supernova explosions. This process of cosmic chemical evolution operates with patient precision, each stellar generation building upon the nucleosynthetic legacy of its predecessors, slowly enriching the interstellar medium with the raw materials necessary for rocky planets and biological chemistry. The galaxy begins with gas clouds composed of roughly 75% hydrogen and 25% helium by mass. The primordial abundances established during Big Bang nucleosynthesis in the universe's first few minutes. Lithium exists in trace amounts. Beryllium and boron remain virtually absent, and no elements heavier than boron exist anywhere in the cosmos. This chemical simplicity defines the initial conditions for stellar nucleosynthesis, creating a blank canvas upon which nuclear processes will gradually paint the periodic table across cosmic time. Population 3, stars the first stellar generation produced the initial heavy elements through nuclear fusion in their cores and explosive nucleosynthesis during their supernova deaths. These massive stars burn hydrogen into helium, then helium into carbon and oxygen, continuing through successive burning stages that produce neon, magnesium, silicon, sulfur, and finally iron peak elements. The core collapse supernovae that end their lives create conditions extreme enough to synthesize elements heavier than iron through rapid neutron capture processes, dispersing these newly forged elements into the surrounding interstellar medium. The enrichment process operates with extreme inefficiency during the galaxy's earliest epochs. Individual population 3 supernovae might enrich gas clouds to metallicities of only 1/10,000th the current solar value, requiring hundreds of supernovae to create chemical compositions capable of supporting the formation of smaller, longer-lived stars. This slow chemical evolution explains why the universe's first billion years produced primarily massive, short-lived stars, with lower mass stellar populations becoming possible only after sufficient heavy element enrichment had occurred. As metallicity increases, the physics of star formation changes dramatically. Heavy elements provide cooling mechanisms that allow gas clouds to radiate away thermal energy more efficiently, enabling gravitational collapse at lower masses and temperatures. Carbon and oxygen, in particular, become crucial coolants that facilitate the formation of molecular hydrogen and other molecules essential for efficient energy dissipation. This enhanced cooling capability gradually shifts the stellar initial mass function toward lower masses, creating stellar populations dominated by long-lived, hydrogen-burning stars. The spatial distribution of heavy elements within the galaxy reflects the history of stellar formation and chemical mixing processes. The galactic bulge and inner disk regions, where star formation began earliest and proceeded most rapidly, achieve higher metallicities than the outer disk and halo. This creates a metallicity gradient that decreases with galactocentric radius, a pattern observed in spiral galaxies throughout the local universe and preserved as a fossil record of chemical evolution timescales. Different stellar mass ranges contribute distinct signatures to the galaxy's chemical enrichment. Massive stars with initial masses exceeding 8 solar masses produce alpha elements: oxygen, neon, magnesium, silicon, sulfur, calcium through hydrostatic burning in their cores. These stars evolve rapidly, completing their life cycles within tens of millions of years and injecting their nucleosynthetic products into the interstellar medium through core collapse supernovae. The alpha element abundances in stellar atmospheres thus reflect the cumulative contribution of massive star nucleosynthesis integrated over cosmic time. Intermediate mass stars, with initial masses between approximately 1 and 8 solar masses, follow longer evolutionary paths that culminate in the formation of white dwarf remnants rather than neutron stars or black holes. During their asymptotic giant branch phases, these stars experience thermal pulses that dredge processed material from their interiors to their surfaces, enabling mass loss through stellar winds. This process enriches the interstellar medium with carbon, nitrogen, and neutron capture elements produced through slow neutron addition processes in stellar interiors, type Ia supernovae, arising from the thermonuclear explosions of white dwarf stars in binary systems, provide the dominant source of iron peak elements in the galaxy. These explosions occur with a characteristic delay time following the initial stellar formation episode, as the white dwarf must first form and then accrete sufficient material from a companion star to trigger the thermonuclear runaway. This delay creates distinct chemical evolution signatures, with alpha to iron ratios decreasing over time as type Ia supernovae begin contributing significant iron to the interstellar medium. The chemical evolution proceeds at different rates in different regions of the galaxy, creating age-metallicity relationships that vary with galactocentric radius and vertical height above the disk plane. The solar neighborhood exhibits a complex age-metallicity relationship with significant scatter, reflecting the stochastic nature of chemical enrichment and the radial migration of stars over their lifetimes. Stars born at different galactocentric radii carry chemical signatures that reflect their birth locations, creating a fossil record of radial abundance gradients that existed at various epochs in galactic history. Galactic chemical evolution models must account for gas flows that redistribute both matter and heavy elements throughout the galaxy. Stellar winds and supernova explosions drive galactic fountains that lift enriched gas above the disk plane before it cools and falls back onto the disk surface. These vertical mixing processes help homogenize chemical abundances within individual disk regions, while maintaining overall radial gradients. Radial gas flows, driven by density waves and gravitational torques, transport enriched material between different galactocentric radii over timescales of hundreds of millions of years. The accretion of pristine gas from the intergalactic medium continues throughout galactic evolution, diluting the heavy element concentrations built up through stellar nucleosynthesis. This gas accretion provides the fuel for continued star formation, while simultaneously reducing the average metallicity of star-forming regions. The balance between metal production through stellar evolution and metal dilution through gas accretion determines the rate of metallicity increase over cosmic time. Inhomogeneous chemical evolution creates localized regions with chemical compositions that deviate significantly from galactic averages. Superbubbles carved by multiple supernovae and stellar associations can concentrate heavy elements to several times the ambient abundance, while regions between star-forming complexes may retain nearly primordial compositions for hundreds of millions of years. This chemical inhomogeneity affects subsequent stellar formation and may contribute to the observed scatter in stellar abundance patterns. The most metal-poor stars observable in the galaxy today preserve chemical compositions that reflect enrichment by only one or a few supernova explosions. These fossil stars, with metallicities less than 1/1000th of solar values, exhibit abundance patterns that allow astronomers to deduce the masses and explosion characteristics of individual population 3 stars. Such observations provide the only direct evidence for the properties of the first stellar generation, whose light has long since faded beyond detectability. Neutron star mergers contribute additional complexity to chemical evolution through R-process nucleosynthesis, rapid neutron capture that produces elements heavier than iron during the extreme conditions of neutron star coalescence. These rare events, occurring perhaps once per 100,000 years in a typical galaxy, produce gold, platinum, europium, and other heavy elements that cannot form through normal stellar evolution processes. The R-process contribution creates distinct chemical signatures in stars that formed from gas enriched by neutron star merger ejecta. Chemical evolution continues today as new stellar generations form from gas enriched to approximately twice the solar metallicity in the galaxy's inner regions. This ongoing enrichment gradually increases the probability of planetary system formation, as higher heavy element abundances facilitate the condensation of rocky material in protoplanetary disks. The chemical evolution of the galaxy thus creates a temporal gradient in planetary formation efficiency. With Earth-like planets becoming more probable in younger stellar systems, modern chemical evolution models incorporate sophisticated treatments of stellar yields, gas dynamics, and mixing processes. Yet significant uncertainties remain regarding the detailed nucleosynthetic contributions of different stellar populations, the relative contributions of various supernova types, the efficiency of chemical mixing processes, and the timescales for gas accretion from the intergalactic medium all influence chemical evolution predictions and remain active areas of research. Only took billions of stellar lifetimes to transform primordial gas into the chemically complex medium that surrounds us today. Only required the patient operation of nuclear fusion and explosive nucleosynthesis to build the periodic table element by element. Only needed the gradual enrichment of interstellar space to create conditions suitable for rocky planets and carbon-based chemistry. The Milky Way's chemical evolution proceeds with inexorable patience, each supernova adding its small contribution to the growing abundance of heavy elements, writing the story of cosmic chemistry and stellar atmospheres that preserve the nuclear ashes of long-dead stars. Around the solar system, stretching outward for hundreds of light-years in every direction, lies a cavity of extraordinary emptiness carved by the violent deaths of nearby stars. The local bubble, a region where the interstellar medium has been heated to millions of degrees and expanded to densities far below the galactic average, surrounds our cosmic neighborhood like a vast, invisible cocoon. Within this rarefied environment, the solar system travels through space that contains fewer than 1 particle per 10 cubic centimeters, a vacuum more complete than anything achievable in terrestrial laboratories, yet filled with the ghostly remnants of stellar explosions that occurred millions of years ago. The local bubble extends approximately 300 light-years in most directions from the solar system, though its boundaries remain irregular and poorly defined due to the complex three-dimensional structure of the interstellar medium. This cavity connects to other similar voids through a network of tunnels and channels that together form what astronomers call the local bubble complex, an interconnected system of hot, low-density regions that may extend for thousands of light-years through the galactic disk. The entire structure resembles a vast sponge, with dense molecular clouds forming the solid framework and hot bubbles representing the empty spaces between. The creation of the local bubble required the combined energy output of dozens of massive stars that lived and died within the past 10 to 15 million years. These stars, originally members of stellar associations and clusters that have since dispersed, injected enormous quantities of mechanical energy into their surroundings through stellar winds and supernova explosions. Each supernova released approximately 10 to the 51st ergs of kinetic energy, equivalent to the total energy output of the Sun over its entire 10 billion year lifetime, into the surrounding interstellar medium within a matter of seconds. Stellar winds from massive stars began the excavation process long before the first supernovae occurred. These winds, driven by radiation pressure and carrying matter away from stellar surfaces at speeds of thousands of kilometers per second, created wind-blown bubbles around individual massive stars. As the winds encountered the ambient interstellar medium, they drove shock waves outward, heating and accelerating the surrounding gas. Multiple wind-blown bubbles from nearby massive stars eventually merged, creating larger cavities that grew over timescales of millions of years. The supernova explosions that followed provided the primary energy source for expanding these cavities to their current dimensions. Each supernova drove a blast wave outward at speeds initially exceeding 10,000 kilometers per second, sweeping up surrounding matter and compressing it into dense shells at the expanding bubble boundaries. The shock waves heated the ambient interstellar medium to temperatures of millions of degrees, hot enough to fully ionize hydrogen and helium and cause the gas to emit X-ray radiation that modern telescopes can detect. The hydrodynamics of bubble expansion follow well-understood physical principles that govern the interaction between blast waves and ambient media. The Seedorf-Taylor blast wave solution describes how supernova remnants expand through uniform media, with the shock radius growing proportionally to time raised to the 2/5 power. However, the local bubble's expansion occurred through a complex, inhomogeneous medium with density variations spanning several orders of magnitude, creating irregular boundaries and non-spherical morphologies that deviate from simple analytical solutions. Radiative cooling eventually slows the expansion of supernova blast waves as the hot gas behind the shocks loses energy through emission of photons. The cooling timescale depends on gas density and temperature, with higher density regions cooling more rapidly due to enhanced collision rates between particles. In the local bubble's low-density environment, radiative cooling operates slowly, allowing the hot gas to remain at million-degree temperatures for tens of millions of years. This extended cooling time maintains the bubble's low density and prevents gravitational collapse back toward the galactic disk's midplane. The local bubble connects to other nearby cavities through tunnels of hot, rarefied gas that thread between denser interstellar clouds. The Lupa superbubble, centered approximately 400 light-years away in the direction of the constellation Scorpius Centaurus, may be connected to the local bubble through such a tunnel. These connections allow hot gas to flow between different cavity systems, creating a network of interconnected voids that extends throughout the local galactic neighborhood. Within the local bubble, the interstellar magnetic field exhibits enhanced strength due to compression and tangling by the multiple shock waves that swept through the region. This magnetic field, threading through the hot plasma, provides additional pressure support that helps maintain the bubble's structure against gravitational collapse. Magneto-hydrodynamic waves propagating through the magnetized plasma create turbulence that further redistributes energy and momentum throughout the cavity. The solar system's location within the local bubble profoundly influences the interstellar environment through which it travels. The solar wind charged particles streaming outward from the Sun at speeds of several hundred kilometers per second encounters the local bubble's hot plasma at the heliopause, the boundary where solar wind pressure balances the pressure of the interstellar medium. Because the local bubble's density is unusually low, this boundary lies farther from the Sun than it would in typical interstellar conditions, extending the solar system's sphere of influence to perhaps 120 astronomical units from the Sun. Cosmic ray propagation through the local bubble differs from that in denser regions of the interstellar medium due to the cavity's unique magnetic field structure and low gas density. Cosmic rays' high-energy particles accelerated by supernova shocks and other energetic processes can travel larger distances before losing energy through interactions with ambient matter. This enhanced cosmic ray propagation may affect the flux of high-energy particles reaching Earth's atmosphere, though the magnitude of this effect remains uncertain. The walls of the local bubble, where the hot interior gas meets the surrounding dense interstellar medium, exhibit complex structure revealed by observations at multiple wavelengths. These boundary regions contain compressed gas, enhanced magnetic fields, and sites of triggered star formation where the shock compression has caused molecular clouds to collapse gravitationally. The Orion star-forming complex, located on the local bubble's boundary, may owe its current activity to compression by the expanding cavity walls. Evidence for the local bubble's existence comes from multiple observational techniques, including measurements of interstellar absorption lines, X-ray emission from hot plasma, and the three-dimensional distribution of nearby dust clouds. The absence of significant dust extinction in most directions within a few hundred light-years of the Sun indicates that normal interstellar matter has been cleared from our immediate vicinity. X-ray observations reveal diffuse emission from million-degree gas that fills the cavity, confirming theoretical predictions for supernova-heated plasma. The age of the local bubble, estimated from the propagation times of blast waves and the cooling ages of the hot plasma, suggests that the most recent major supernova explosions occurred between 2 and 5 million years ago. This timing coincides with epochs of enhanced cosmic ray flux recorded in deep-sea sediments on Earth, suggesting that nearby supernovae may have influenced terrestrial climate and evolution through increased atmospheric ionization and cloud formation processes. Future evolution of the local bubble depends on the continued energy input from stellar sources and the gradual cooling of the hot interior plasma. Without additional supernova explosions to maintain the high temperature and low density, the bubble will slowly contract as radiative cooling allows the hot gas to condense and fall back toward the galactic disk. This process operates on timescales of tens of millions of years, much longer than the intervals between supernova explosions in typical stellar associations. The local bubble serves as a natural laboratory for studying superbubble physics and the effects of stellar feedback on the interstellar medium. Similar cavities exist throughout the galaxy, carved by stellar associations and supernova explosions in all regions where massive star formation has occurred. These bubbles play crucial roles in regulating star formation, driving galactic fountains that lift enriched gas above the disk plane, and creating the complex, multi-phase structure observed in the interstellar medium. Archaeological evidence preserved in the local bubble structure provides clues about the stellar populations responsible for its creation. The cavity's orientation and morphology suggest that the primary energy sources were associated with the Scosen Association and other nearby groups of massive stars that formed from giant molecular clouds 10 to 20 million years ago. Stellar remnants from these explosions, neutron stars, and stellar mass black holes may still orbit within the local bubble, though their detection remains challenging due to their intrinsic faintness. The connection between the local bubble and other nearby cavities creates a network of hot, low-density channels that may facilitate the transport of matter and energy over large distances within the galactic disk. This network structure affects the propagation of cosmic rays, the distribution of heavy elements produced by stellar nucleosynthesis, and the global circulation patterns that regulate star formation throughout the galaxy. Only took the deaths of a few dozen massive stars to carve a cavity hundreds of light years across. Only required the concentrated energy of multiple supernovae to create the rarefied environment through which the solar system travels. Only needed the violent finale of stellar evolution to provide the solar system with a cosmic haven, a bubble of emptiness that shields us from the denser, more turbulent regions of the interstellar medium, a testament to the power of stellar explosions to reshape space on scales that dwarf individual stellar systems, creating structure through destruction and order through chaos. Within the vast spiral arms of the Milky Way, stellar nurseries pulse with rhythmic activity that spans millions of years, creating waves of stellar birth that sweep through molecular cloud complexes like tides across a cosmic shore. Giant molecular clouds, sprawling collections of hydrogen gas and dust that can contain hundreds of thousands of solar masses, collapse under their own gravity in episodes that transform diffuse interstellar matter into dense clusters of newly formed stars. This process of star formation operates with cyclical precision, governed by the interplay between gravitational attraction, turbulent motion, magnetic fields, and stellar feedback that creates a complex dance of creation and destruction across galactic timescales. The molecular clouds that serve as stellar nurseries exist in a delicate balance between forces that promote collapse and those that resist it. Gravity pulls inward, attempting to compress the gas to densities high enough for stellar formation, while thermal pressure, turbulent motion, and magnetic fields provide outward support that can halt or delay gravitational contraction. The critical density for gravitational instability depends on temperature and the strength of magnetic support, typically requiring gas densities of at least several hundred particles per cubic centimeter before self-gravity can overcome the opposing forces. Turbulence within molecular clouds creates a complex hierarchy of structure, with dense clumps and filaments embedded within lower density environments. This turbulent cascade, driven by a combination of gravitational instabilities, stellar winds, supernova explosions, and galactic rotation, generates density fluctuations across spatial scales ranging from entire cloud complexes down to individual stellar cores. The turbulent energy dissipates over timescales of several million years, requiring continuous replenishment through external energy sources to maintain the observed velocity dispersions. Magnetic fields threading through molecular clouds provide crucial support against gravitational collapse, particularly in the early stages of cloud evolution when gas densities remain relatively low. The magnetic pressure and tension forces can support clouds against gravity for timescales much longer than the freefall collapse time, allowing clouds to persist for tens of millions of years before fragmentation and stellar formation begin. However, as gravitational contraction proceeds, the magnetic field lines become increasingly tangled and compressed, eventually losing their ability to prevent collapse. The fragmentation of molecular clouds into stellar mass cores occurs through gravitational instabilities that develop on the Jeans length scale, the characteristic size over which gravity can overcome pressure support. As cloud densities increase during the early stages of collapse, the Jeans length decreases, allowing smaller and smaller structures to become gravitationally unstable. This hierarchical fragmentation process naturally leads to the formation of stellar clusters, as individual stellar cores condense from the same parent cloud and retain their spatial association over timescales of millions of years. Stellar feedback from newly formed massive stars profoundly influences the subsequent evolution of their parent molecular clouds. Intense ultraviolet radiation from hot, young stars ionizes surrounding hydrogen gas, creating H2 regions, bubbles of ionized plasma that expand at speeds of approximately 10 km per second into the neutral molecular material. The pressure from this ionized gas compresses adjacent neutral regions, potentially triggering new episodes of gravitational collapse and stellar formation in a process called triggered star formation. Stellar winds from massive stars inject mechanical energy into molecular clouds at rates that can exceed the gravitational binding energy of the entire cloud complex. These winds, carrying matter away from stellar surfaces at speeds of thousands of kilometers per second, carve cavities within the molecular material and drive turbulent motions that can either enhance or suppress further star formation depending on the detailed dynamics. The combined effects of radiation pressure, photoionization, and stellar winds create complex feedback loops that regulate the efficiency and duration of stellar formation episodes. Supernova explosions provide the ultimate form of stellar feedback, injecting approximately 10 to the 51st ergs of kinetic energy into their surroundings within seconds of core collapse. A single supernova can disrupt an entire molecular cloud complex, dispersing the remaining gas and halting further star formation for millions of years. However, the shockwaves driven by supernova explosions can also compress distant molecular clouds, triggering new rounds of stellar birth in regions far from the original explosion site. The stellar initial mass function, the distribution of masses among newly formed stars, exhibits remarkable universality across different star-forming environments within the galaxy. This universal distribution, characterized by a preponderance of low-mass stars and a smaller population of high-mass objects, suggests that fundamental physical processes governing stellar formation operate similarly in widely different conditions. The EF slope for masses above approximately 1 solar mass follows a power law, with index approximately -2.3, known as the salpeter slope, while lower masses exhibit a flattening that creates a characteristic peak around 0.3 solar masses. Brown dwarfs objects with masses below the hydrogen burning threshold of approximately 0.08 solar masses form through the same gravitational collapse processes that create normal stars but lack sufficient mass to sustain nuclear fusion in their cores. These failed stars cool continuously throughout their lifetimes, fading from initial temperatures of thousands of Kelvin to eventual surface temperatures comparable to planetary atmospheres. The brown dwarf population provides crucial tests of stellar formation theories and the low-mass end of the initial mass function. Protoplanetary disks around newly formed stars preserve the angular momentum of the original molecular cloud material, creating flattened structures within which planetary systems eventually form. The lifetime of these disks, typically several million years, is determined by the balance between viscous accretion that transports matter inward toward the central star and photoevaporation driven by stellar radiation that disperses the disk material. The disk dispersal timescale sets important constraints on planetary formation processes and the final architecture of planetary systems. Binary and multiple star systems form frequently during the stellar formation process, with perhaps half of all stellar systems containing more than one star. The formation of binary systems occurs through several mechanisms, including the fragmentation of rotating protostellar cores, capture of stars during close encounters in dense stellar clusters, and the gravitational contraction of wide binary systems formed from separate condensations within the same molecular cloud. The properties of binary systems, orbital periods, mass ratios, eccentricities preserve information about the conditions and processes operating during stellar formation. star formation efficiency in molecular clouds typically remains low, with only a few % of the available gas mass converted into stars before stellar feedback disrupts the remaining material. This low efficiency results from the complex interplay between gravity, turbulence, magnetic fields, and stellar feedback that creates a self-regulating system where star formation automatically generates the conditions necessary to halt further collapse. The remaining gas disperses into the interstellar medium, where it may eventually participate in future episodes of star formation after cooling and reaccumulating into new molecular cloud complexes. The clustering properties of newly formed stars reflect the hierarchical structure of their parent molecular clouds and the gravitational dynamics operating during the formation process. Most stars form in gravitationally bound clusters containing hundreds to thousands of members, though the majority of these clusters dissolve within a few tens of millions of years as stellar evolution and galactic tidal forces gradually disperse their constituent stars. Only the most massive clusters survive as bound stellar associations for hundreds of millions of years. Observations of star-forming regions throughout the galaxy reveal a correlation between the star formation rate and the surface density of molecular gas, known as the Kennicutt-Schmidt law. This empirical relationship suggests that star formation operates as a threshold phenomenon, with significant stellar birth occurring only when gas surface densities exceed critical values of approximately 10 solar masses per square parsec. Below this threshold, turbulent and magnetic support can prevent gravitational collapse indefinitely. The galactic distribution of star formation follows the spiral arm pattern, with enhanced stellar birth rates occurring in regions where spiral density waves compress molecular clouds and trigger gravitational instabilities. However, star formation also occurs in interarm regions, creating a more complex spatial distribution that reflects the stochastic nature of molecular cloud formation and evolution. The overall galactic star formation rate has declined by factors of several since the universe's peak epoch of stellar birth, approximately 10 billion years ago. Chemical abundance patterns in newly formed stars reflect the metallicity of their parent molecular clouds and provide fossil records of previous episodes of stellar evolution and nucleosynthesis. The gradual increase in heavy element abundances over cosmic time affects both the star formation process itself through enhanced cooling and opacity effects and the properties of the resulting stellar populations. Higher metallicity environments tend to produce stellar populations with enhanced numbers of low-mass stars and more efficient planetary formation processes. Only took the patient balance between gravity and turbulence to create the conditions for stellar birth. Only required the complex interplay of physical processes operating across vast ranges of scale and time to transform diffuse gas into concentrated stellar energy sources. Only needed the rhythmic pulsing of creation and destruction to maintain the galaxy's stellar population across cosmic ages. Star formation proceeds through cycles that span millions of years, molecular clouds breathing in rhythm with galactic rotation, each breath creating new suns that will burn for billions of years, carrying forward the chemical legacy of all previous stellar generations, while adding their own contributions to the galaxy's evolving composition. Through the vast architecture of the Milky Way, the solar system traces an enormous elliptical path that carries Earth and its companion worlds on a journey of unimaginable duration and scale. One complete orbit around the galactic center requires approximately 230 million years, a period astronomers call a galactic year or cosmic year. During this stately procession through space, the solar system travels at an average velocity of 220 kilometers per second relative to the galactic center, moving fast enough to circle Earth's equator in less than 3 minutes, yet requiring nearly 250 million years to complete a single circuit of the galaxy. The solar system currently resides approximately 26,000 light-years from the galactic center, positioned within what astronomers call the galactic habitable zone, a region where conditions favor the development and persistence of life. This orbital radius places the solar system between the major spiral arms in a relatively quiet region, where the frequency of disruptive events remains lower than in the spiral arms themselves or in the more chaotic inner regions of the galaxy. The orbital path carries the solar system through varying galactic environments over the course of each galactic year, creating cosmic seasons that influence conditions throughout the solar system. During its orbital journey, the solar system experiences periodic passages through spiral arms, regions of enhanced stellar density where massive stars and their associated supernova explosions occur more frequently than in interarm regions. These spiral arm crossings happen approximately every 100 million years, exposing Earth to increased levels of cosmic radiation and potentially triggering ice ages through enhanced cloud formation in the upper atmosphere. The most recent spiral arm passage may have occurred during the Cretaceous period, roughly coinciding with the mass extinction event that ended the age of dinosaurs. The galactic orbit exhibits a complex three-dimensional character that carries the solar system above and below the galactic disk plane in oscillations that repeat approximately every 64 million years. Currently, the solar system lies approximately 27 light-years above the galactic midplane and is moving upward at a velocity of 7 kilometers per second. The system will continue rising for another 14 million years before reaching maximum height above the disk, then begin falling back toward the midplane in an oscillatory motion that has persisted throughout the solar system's history. These vertical oscillations through the galactic disk expose the solar system to varying densities of interstellar matter, cosmic rays, and gravitational perturbations from nearby stellar populations. The passages through the dense galactic midplane, occurring roughly every 32 million years, coincide with periods of increased comet flux from the outer solar system, as gravitational interactions with molecular clouds and dark matter concentrations perturb the orbits of objects in the Oort cloud. Some researchers have proposed correlations between these midplane crossings and mass extinction events in Earth's fossil record, though the evidence remains inconclusive. The solar system's orbital velocity varies slightly as it moves through regions of different gravitational potential within the galaxy. When travelling through the inner regions of its elliptical orbit, closer to concentrations of stellar mass, the system moves faster according to Kepler's laws of orbital motion. Conversely, during passages through the outer regions of the orbit, where the local gravitational field strength decreases, the orbital velocity diminishes correspondingly. These velocity variations amount to several kilometers per second over the course of a complete galactic year. Gravitational interactions with nearby stars and stellar associations cause small but cumulative changes in the solar system's orbital parameters over cosmic timescales. Close passages of other stellar systems, occurring perhaps once every million years within distances of a few light-years, exert gravitational perturbations that can alter the solar system's orbital eccentricity, inclination, and angular momentum. These stellar encounters represent a form of gravitational weather that gradually evolves the orbital characteristics over many galactic years, the local standard of rest. The average motion of nearby stars relative to the galactic center provides a reference frame for measuring the solar system's peculiar motion through the local galactic neighborhood. The Sun currently moves at approximately 13 kilometers per second relative to this local standard, heading in the direction of the constellation Hercules in what astronomers call the solar apex. This peculiar motion reflects the solar system's formation from a molecular cloud that possessed its own distinctive velocity relative to the galactic rotation pattern. As the solar system orbits the galaxy, it encounters varying densities of interstellar matter that influence the heliosphere, the bubble of charged particles blown outward by the solar wind. Passages through denser molecular clouds compress the heliosphere and allow more interstellar material to penetrate closer to the inner planets, potentially affecting atmospheric chemistry and climate patterns on Earth. The solar system may have entered such dense regions several times during its orbital history, creating episodes of enhanced atmospheric interaction with interstellar matter. The changing galactic environment encountered during orbital motion affects the flux of cosmic rays reaching the solar system. Cosmic rays, high-energy particles accelerated by supernova shocks and other energetic processes, are partially deflected by the solar magnetic field and the heliosphere, but their overall intensity varies with the local density of sources and the magnetic field structure of the interstellar medium. Higher cosmic ray fluxes during spiral arm passages may enhance atmospheric ionization and influence cloud formation processes on Earth. Gravitational tides from the galaxy's non-spherical mass distribution create small but measurable effects on solar system dynamics over very long timescales. The differential gravitational field experienced by objects at different distances from the galactic center generates tidal forces that can perturb the orbits of long-period comets and trans-Neptunian objects. These galactic tides may play a role in determining the outer boundary of the solar system's gravitational sphere of influence and the long-term stability of the Oort cloud. The solar system's orbital motion through the galaxy's rotating reference frame creates apparent forces analogous to the Coriolis effect experienced on rotating planets. These fictitious forces, arising from the non-inertial nature of the galactic coordinate system, influence the motion of interstellar gas and dust relative to the solar system, and contribute to the complex dynamics of material exchange between stellar systems and the interstellar medium. During its galactic journey, the solar system occasionally encounters stellar streams, coherent groups of stars that share similar orbital characteristics due to their common origin in disrupted star clusters or dwarf galaxies. These encounters provide opportunities for enhanced gravitational interactions and may contribute to the solar system's gradual orbital evolution over cosmic timescales. Some stellar streams contain hundreds of individual stars stretched along orbital paths that span hundreds of light years. The solar system's current position within the local bubble, a cavity of hot, low-density gas carved by nearby supernova explosions, represents a temporary phase in its galactic journey. Future orbital motion will eventually carry the system out of this rarefied environment and into regions of higher interstellar density, potentially compressing the heliosphere and altering the interstellar boundary conditions that currently characterize the outer solar system. Radial migration processes can cause stellar systems to change their orbital radii over cosmic timescales through gravitational interactions with spiral density waves and other non-axis symmetric features of the galactic potential. The solar system may have formed at a different galactocentric radius and subsequently migrated to its current position through such processes, carrying with it the chemical signatures of its birth environment, preserved in the compositions of meteorites and planetary atmospheres. The metallicity gradient observed in the galactic disk, the systematic decrease in heavy element abundances with increasing distance from the galactic center, suggests that the solar system's current orbital radius corresponds to a region where the interstellar medium possesses approximately solar chemical composition. This concordance may be coincidental, or may reflect migration processes that carried the solar system to a radius appropriate for its formation metallicity. Future evolution of the solar system's galactic orbit will be influenced by the gradually changing gravitational potential of the galaxy as stellar evolution, gas accretion, and mergers with satellite galaxies modify the distribution of mass within the Milky Way. The anticipated collision with the Andromeda Galaxy in approximately 4.5 billion years will dramatically alter the gravitational environment and likely scatter the solar system into a new orbital configuration within the merged galaxy system. Observations of exoplanetary systems throughout the galaxy reveal that stellar systems orbiting at various galactocentric radii can successfully maintain stable planetary configurations over cosmic timescales. The galactic habitable zone concept, while useful for statistical studies, does not preclude the existence of life-bearing worlds in other galactic environments. As local conditions around individual stars may be more important than large-scale galactic properties for determining habitability, only took 230 million years for the solar system to complete its grand circuit of the galaxy, only required the patient operation of gravitational dynamics to maintain stable orbital motion across cosmic ages, only needed the galaxy's orderly rotation to provide a framework for solar system evolution over timescales that encompass the entire history of complex life on Earth. The galactic year proceeds with mechanical precision, carrying the solar system through changing cosmic environments that influence planetary climates and evolutionary processes, marking time on scales so vast that entire geological epochs represent mere moments in the galaxy's stately rotation. Through the vast halo of the Milky Way, ghostly rivers of stars trace the orbital paths of galaxies that no longer exist. Stellar streams long, thin distributions of stars stretched across tens of thousands of light years mark the gravitational dissolution of smaller galactic systems that venture too close to the Milky Way's immense tidal field. These stellar fossils preserve the archaeological record of galactic cannibalism, each stream representing the dismembered remains of a dwarf galaxy or globular cluster that has been torn apart by differential gravitational forces operating over hundreds of millions of years. The process of tidal disruption operates with inexorable efficiency as satellite galaxies orbit within the Milky Way's extended gravitational influence. Tidal forces arise from the differential gravitational acceleration experienced by different parts of an extended object moving through a non-uniform gravitational field. Stars on the near side of a satellite galaxy experience stronger gravitational attraction toward the Milky Way's center than stars on the far side. creating a stretching force that gradually overcomes the satellite's internal gravitational binding and pulls the system apart along its orbital direction. The Sagittarius dwarf galaxy provides the most dramatic example of ongoing tidal disruption within the local group. This small elliptical system, containing perhaps 10 billion solar masses of stars and dark matter, currently lies approximately 25,000 light-years from the Milky Way's centre on a highly eccentric orbit that carries it from the outer halo to within the galactic disk. Multiple passages through the Milky Way's inner regions over the past few billion years have stripped away most of the galaxy's stellar population, creating leading and trailing tidal tails that wrap around the entire Milky Way multiple times. The Sagittarius stream extends across more than 360 degrees of sky as seen from Earth, making it the largest coherent structure visible in the galaxy's stellar halo. Computer simulations of the disruption process reveal that the stream contains stars stripped during multiple pericentric passages, with different portions of the stream corresponding to material lost during different orbital cycles. The stream's complex morphology, including gaps, braiding, and bifurcations, reflects the complicated dynamics of tidal stripping in the time-varying gravitational potential of the galaxy. Observational surveys have identified dozens of additional stellar streams throughout the Milky Way's halo, each representing the tidal remnant of a disrupted satellite system. The GD1 stream stretches across more than 60 degrees of sky in the constellation of Lynx, likely originating from a globular cluster disrupted several hundred million years ago. The PAL-5 stream traces the orbital path of the globular cluster Palomar 5, which continues to lose stars through tidal stripping as it orbits the galaxy every 200 million years. The discovery of stellar streams relies on sophisticated observational techniques that can identify coherent patterns in the six-dimensional phase space of stellar positions and velocities. Stars within a stream share similar orbital characteristics inherited from their parent system, creating kinematic signatures that distinguish stream members from the more randomly distributed field halo population. Modern astrometric surveys, particularly the European Space Agency's Gaia mission, have revolutionized stream detection by providing precise measurements of stellar proper motions across large areas of sky. The morphology of stellar streams provides powerful constraints on the galaxy's gravitational potential and dark matter distribution. The precise shape of a tidal stream depends sensitively on the mass distribution through which the progenitor system orbited, making streams natural probes of galactic structure. Deviations from smooth stream morphology, such as gaps, spurs, or density variations, can reveal the presence of dark matter, subhalos, or other gravitational perturbations that influence the stream's evolution. Cold, stellar streams, characterized by very small velocity dispersions perpendicular to their orbital paths, preserve information about the internal structure and dynamics of their progenitor systems. Streams originating from globular clusters typically exhibit smaller velocity dispersions than those arising from dwarf galaxies, reflecting the more tightly bound nature of cluster systems. The velocity dispersion along a stream also varies with position, generally increasing with distance from the progenitor due to the longer time available for gravitational perturbations to act. Dark matter substructure within the galactic halo creates gravitational perturbations that can significantly modify stellar stream properties over cosmic timescales. Computer simulations predict that the Milky Way's dark matter halo contains thousands of subhalos-bound concentrations of dark matter that survived the galaxy formation process as fossil remnants of smaller systems that merged with the proto-Milky Way. These invisible structures, ranging in mass from millions to billions of solar masses, act as gravitational lenses that deflect stream stars and create observable distortions in stream morphology. The heating of stellar streams by encounters with dark matter subhalos provides one of the most promising methods for detecting dark matter structure on scales much smaller than typical dwarf galaxies. A close encounter between a stream and a massive subhalo creates characteristic signatures, gaps in the stream density, increases in velocity dispersion, and changes in the stream's orbital energy that persist for hundreds of millions of years after the interaction. Statistical analysis of these perturbations can constrain the abundance and mass function of dark matter substructure throughout the galactic halo. The chemical compositions of stream stars preserve fossil records of the nucleosynthetic history within their parent systems. Dwarf galaxies typically exhibit lower metallicities and different abundance patterns compared to Milky Way stars. reflecting their distinct star formation histories and chemical evolution pathways. Stream stars thus carry chemical tags that identify their extragalactic origin and provide insights into the properties of the satellite systems that contributed to the galaxy's assembly. Multiple stellar populations within individual streams can reveal the complex star formation histories of their progenitor systems. Some streams contain stars with different ages and metallicities, indicating that their parent galaxies experienced extended periods of star formation before tidal disruption. The most metal-poor stream stars may preserve the chemical signatures of the first stellar generations within their host systems, providing windows into the early universe's star formation processes. The spatial distribution of stellar streams throughout the galactic halo reflects the orbital characteristics of the satellite systems from which they originated. Streams on highly eccentric orbits create more extended structures that can reach large distances from the galactic center, while those on more circular orbits remain confined to smaller galactocentric radii. The overall pattern of stream orientations provides statistical constraints on the accretion history and merger tree of the Milky Way's formation. Some stellar streams exhibit gaps or density variations that cannot be explained by encounters with known gravitational perturbers. These unexplained features may indicate the presence of intermediate mass black holes objects with masses between stellar remnants and supermassive galactic nuclei that were ejected from the centers of disrupted dwarf galaxies. Alternative explanations include encounters with very low-mass dark matter subhalos that contain insufficient ordinary matter to form visible stellar populations. The rate of stellar stream formation within the local group appears to have varied over cosmic time, with enhanced activity during epochs when satellite galaxies were more numerous and the galaxy's tidal field was less developed. The current population of observable streams represents only a small fraction of the total number of satellite systems that have been disrupted over the Milky Way's lifetime. As streams gradually fade and disperse due to phase mixing and gravitational heating processes, future observations with next-generation telescopes and survey programs will dramatically expand the census of stellar streams and enable detailed studies of their internal structure and dynamics. Wide-field spectroscopic surveys will measure radial velocities for millions of stream stars, providing complete six-dimensional phase space information that can be used to reconstruct the orbital histories and progenitor properties of disrupted systems. The connection between stellar streams and the broader context of galaxy formation provides insights into the hierarchical assembly process that built massive galaxies like the Milky Way from smaller building blocks. The total mass in stellar streams throughout the galactic halo amounts to perhaps 1% of the galaxy's stellar mass, suggesting that accretion of satellite systems contributed significantly to the outer regions of the galaxy's stellar distribution, while having minimal impact on the central disk and bulge components. Numerical simulations of galaxy formation in cosmological contexts predict that stellar streams should be common features in the halos of massive spiral galaxies throughout the universe. The Milky Way's stream population thus provides a local laboratory for testing theoretical predictions of hierarchical structure formation and the role of minor mergers in galaxy evolution. These fossil records of galactic cannibalism preserve the memory of cosmic assembly processes operating over billions of years. Only took the patient operation of tidal forces to transform entire galaxies into sparse streams of stars. Only required the differential pull of gravity to stretch satellite systems across vast distances while preserving their orbital coherence. Only needed the Milky Way's inexorable appetite for smaller companions to create the ghostly rivers that trace ancient destruction throughout the galactic halo. Stellar streams flow through space like celestial tributaries, carrying the dismembered remains of forgotten worlds, their trajectories marking the paths of galaxies that once burned with their own stellar fires, but now exist only as scattered lights following the gravitational memory of their final orbits. Through the vast spaces between stars, invisible threads of magnetic force weave a complex tapestry that spans the entire galaxy. The Milky Way's magnetic field, though millions of times weaker than Earth's surface magnetism, extends across hundreds of thousands of light-years, threading through interstellar gas clouds, guiding the motion of charged particles, and influencing processes from stellar formation to cosmic ray propagation. This galactic magnetic architecture operates as a largely unseen infrastructure that shapes the behavior of ionized matter throughout the galaxy, creating structure and imposing order on scales that dwarf individual stellar systems. The magnetic field strength varies dramatically throughout different regions of the galaxy, ranging from approximately 1 microgauss in the tenuous outer halo to perhaps 1,000 microgauss in the dense cores of molecular clouds. For comparison, Earth's magnetic field measures roughly half a Gauss at the planet's surface, making even the strongest galactic magnetic fields millions of times weaker than typical terrestrial values. Despite this apparent weakness, the magnetic field's influence becomes significant when operating over the enormous volumes of space that comprise galactic structures. Observations reveal that the galactic magnetic field exhibits a complex, multi-component structure that includes both large-scale ordered components and smaller-scale turbulent variations. The large-scale field appears to follow a spiral pattern that correlates loosely with the galaxy's spiral arm structure. Though the magnetic spiral arms do not coincide exactly with the stellar spiral arms, this magnetic spiral likely results from the differential rotation of the galaxy, which winds up initially poloidal magnetic field lines into predominantly azimuthal configurations over cosmic timescales. The origin of the galactic magnetic field remains one of astrophysics' outstanding puzzles. Seed magnetic fields may have been present in the primordial gas from which the galaxy formed, perhaps generated during the early universe's inflationary epoch, or by processes operating in the first generation of stars and galaxies. Alternatively, seed fields might have been created by battery mechanisms operating during the galaxy's formation, such as the Biermann battery effect, which can generate weak magnetic fields through the misalignment of pressure and density gradients in ionized plasmas. Once established, even extremely weak seed magnetic fields can be amplified to observed levels through dynamo processes operating over cosmic timescales. The galactic dynamo mechanism involves the interaction between differential rotation and turbulent convection within the ionized interstellar medium, creating a feedback loop where existing magnetic fields are stretched and twisted by bulk motions of the plasma. Alpha-omega dynamos, named for the types of velocity fields involved, can amplify initial magnetic field strengths by factors of billions over the galaxy's lifetime. The galactic magnetic field plays crucial roles in regulating star formation throughout the galaxy by providing additional pressure support against gravitational collapse in molecular clouds. Magnetic pressure and tension forces can support clouds against their own gravity for extended periods, delaying the onset of stellar formation until other processes such as turbulent decay or external triggers overcome the magnetic support. This magnetic regulation helps explain the observed low efficiency of star formation in molecular clouds. Magnetic fields also influence the morphology and dynamics of stellar formation processes. Once gravitational collapse begins, the magnetic field threading through a collapsing molecular cloud core must be partially removed or redistributed to allow matter to reach the high densities required for stellar ignition. This process, known as magnetic flux loss, occurs through ambipolar diffusion, the gradual drift of neutral gas through the magnetic field lines that remain tied to the ionized component of the molecular medium. The alignment of magnetic field lines affects the formation of protostellar disks around newly forming stars. Strong magnetic fields can prevent the formation of large, extended disks by removing angular momentum from infalling material, while weaker fields allow more massive disks to form. This magnetic influence on disk formation has important implications for planetary system architecture and the frequency of different types of exoplanetary systems throughout the galaxy. Cosmic rays' high-energy charged particles that pervade the galaxy interact strongly with the galactic magnetic field, which confines their propagation and influences their distribution throughout interstellar space. The magnetic field acts as a complex maze that scatters cosmic ray particles, causing them to diffuse slowly through the galaxy rather than traveling in straight lines. This magnetic confinement increases the time cosmic rays spend in the galaxy, enhancing their interactions with interstellar matter and affecting their observed energy spectrum and spatial distribution. The galactic magnetic field channels cosmic rays along field lines, creating preferred directions for particle propagation that can lead to anisotropies in the cosmic ray distribution. These anisotropies, though small in amplitude, provide observational signatures that allow astronomers to probe the magnetic field structure throughout the galaxy. The correlation between cosmic ray intensity variations and magnetic field geometry offers insights into both cosmic ray origins and magnetic field configurations in regions too distant for direct measurement. Faraday rotation of polarized radio waves provides one of the most powerful techniques for mapping the galactic magnetic field structure. As polarized electromagnetic radiation travels through the magnetized interstellar medium, the plane of polarization rotates by an amount proportional to the integral of the magnetic field strength along the line of sight. Observations of this Faraday rotation toward pulsars and background radio galaxies reveal the magnetic field structure throughout the galactic disk and halo. Synchrotron radiation from relativistic electrons spiraling in the galactic magnetic field creates a diffuse radio background that traces the magnetic field distribution throughout the galaxy. The intensity and polarization properties of this synchrotron emission depend on both the magnetic field strength and the population of high-energy electrons, providing complementary information about galactic magnetic field properties. Multi-frequency radio observations can separate synchrotron emission from other radio sources and map magnetic field variations across the galactic disk. Dust grains in the interstellar medium become aligned with magnetic field lines through various physical mechanisms, creating systematic patterns in the polarization of starlight that reveal magnetic field orientations in nearby regions of the galaxy. These optical and infrared polarization measurements complement radio techniques by probing magnetic fields in dense molecular clouds and dust lanes where radio waves cannot penetrate. The combination of different observational approaches provides a comprehensive picture of magnetic field structure across diverse galactic environments. The galactic magnetic field influences the dynamics of supernova remnants and stellar wind bubbles by providing additional pressure that can confine or channel the expanding shock waves. Magnetic pressure can cause supernova remnants to preferentially expand along field lines, creating elongated structures that trace the local magnetic field geometry. These interactions between explosive stellar events and magnetic fields contribute to the complex morphologies observed in supernova remnants throughout the galaxy. Magnetohydrodynamic waves. Oscillations in magnetized plasma propagate through the galactic magnetic field, transporting energy and momentum across vast distances within the interstellar medium. Alphen waves, in particular, can travel along magnetic field lines at speeds determined by the field strength and plasma density, providing mechanisms for coupling processes occurring in widely separated regions of the galaxy. These magnetic waves may play important roles in heating the interstellar medium and driving turbulence in molecular clouds. The magnetic field geometry affects the formation and evolution of galactic structures, such as spiral arms and bars. Magnetic stresses can influence the propagation of density waves through the galactic disk, potentially modifying the spiral arm pattern and affecting star formation rates within the arms. Magnetorotational instabilities may contribute to the angular momentum transport that allows gas to flow inward through the galactic disk, feeding the central regions and influencing the galaxy's long-term evolution. Parker instabilities develop in the galactic disk where magnetic pressure and cosmic ray pressure create buoyant irregularities that can rise above the disk plane, forming loops and arches in the magnetic field structure. These magnetic buoyancy effects may contribute to the formation of superbubbles and chimneys that transport matter and energy between the disk and halo components of the galaxy. The resulting magnetic field morphology exhibits complex three-dimensional structure that influences particle propagation and energy transport throughout the galactic system. Intergalactic magnetic fields may connect the Milky Way's magnetosphere to those of neighboring galaxies, creating a cosmic web of magnetic structure that extends throughout the local group. These weak extragalactic fields, if they exist, could influence the escape of cosmic rays from individual galaxies and affect the propagation of high-energy particles on scales comparable to galaxy clusters. The detection and characterization of intergalactic magnetic fields remains an active area of observational and theoretical research. The temporal evolution of the galactic magnetic field over cosmic timescales remains poorly understood, though numerical simulations suggest that field configurations can change significantly over periods comparable to the galaxy's age. Interactions with satellite galaxies, variations in star formation rates, and changes in the galaxy's rotation pattern all potentially influence magnetic field evolution. The current magnetic field structure thus represents a snapshot of an evolving system that has been shaped by billions of years of galactic dynamics. Only took the amplification of primordial seed fields to create magnetic structure spanning the entire galaxy. Only required the patient operation of dynamo processes to transform weak initial magnetism into the complex field geometry observed today. only needed the invisible architecture of magnetic force to influence virtually every astrophysical process operating within galactic environments. The galactic magnetic field threads through space like a cosmic nervous system, connecting distant regions through invisible channels that guide charged particles, shape stellar formation, and impose subtle order on the apparent chaos of interstellar space, demonstrating that magnetism operates as a fundamental organizing principle throughout the universe. In the vast darkness of intergalactic space, two spiral galaxies drift toward each other with inexorable certainty, their gravitational dance spanning billions of years and culminating in one of the most spectacular events the local universe will ever witness. The Milky Way and Andromeda Galaxy M31 to astronomers approach each other at a velocity of approximately 110 kilometers per second, a cosmic collision course that will bring these galactic giants together in roughly 4.5 billion years. This future merger represents not destruction, but transformation, as two mature spiral systems combine to create something entirely new, a massive elliptical galaxy that astronomers have already named Milkomeda. The Andromeda Galaxy, located approximately 2.5 million light-years from the Milky Way, contains roughly 1 trillion stars compared to our galaxy's estimated 400 billion, making it the most massive member of the local group. Despite its greater stellar population, Andromeda exhibits a structure remarkably similar to the Milky Way, a central bulge surrounded by spiral arms embedded within an extended dark matter halo. Both galaxies have likely grown through the accretion of smaller satellite systems over cosmic time, creating the complex stellar populations and substructures observed today. Computer simulations of the collision reveal a complex gravitational ballet that unfolds over several billion years. The first close encounter between the galaxies will occur approximately 4.5 billion years from now, though the actual merger process will require multiple passages and gravitational interactions before the systems settle into their final configuration. During the initial approach, tidal forces will begin to distort both galaxies, creating spectacular streams and tails of stars that extend for hundreds of thousands of light-years beyond the main galactic bodies. The orbital dynamics governing the merger depend critically on the relative velocities, impact parameter, and dark matter halo properties of both galaxies. Current observations suggest a nearly head-on collision, though uncertainties in Andromeda's transverse velocity allow for a range of possible encounter geometries. A direct collision would create the most dramatic tidal disruption and rapid merger timescale, while a more glancing encounter might result in a longer, more gradual coalescence process extending over 10 billion years. Despite the name collision, the merger will not involve direct impacts between individual stars due to the vast spaces separating stellar systems within each galaxy. The probability of stellar collisions during the merger remains negligibly small, with typical separations between stars exceeding the stellar cross-sectional areas by factors of trillions. Instead, stars will be scattered into new orbital configurations by the changing gravitational potential as the two galaxies interpenetrate and merge, creating a violent relaxation process that redistributes stellar orbits throughout the combined system. The supermassive black holes at the centers of both galaxies, Sagittarius A in the Milky Way and the similar mass central black hole in Andromeda, will eventually spiral toward each other and merge in one of the most energetic events possible in the universe. This black hole merger will release enormous amounts of energy in the form of gravitational waves, electromagnetic radiation, and high-energy particle acceleration. The final black hole, containing approximately 8 million solar masses, will recoil from the gravitational wave emission and may be ejected from the galactic center entirely. Star formation rates during the merger will likely increase dramatically as gravitational interactions compress molecular gas clouds and trigger enhanced stellar birth. The collision will drive gas flows toward the central regions of the merging system, fueling both star formation and growth of the central black holes. These processes may create a period of intense starburst activity that consumes much of the available gas supply within a few 100 million years, leaving the final merged galaxy relatively quiescent compared to present-day spiral systems. The morphological transformation from two spiral galaxies to a single elliptical system occurs through the destruction of ordered rotation and the establishment of more randomly oriented stellar orbits. The collision scrambles the organized disk structures of both galaxies, converting their rotational kinetic energy into random motion that supports a roughly spherical mass distribution. The final elliptical galaxy will likely exhibit little net rotation and will lack the spiral arm structure that characterizes both progenitor systems. Tidal tails created during the merger process will extend far beyond the main body of the combined galaxy, creating streams of stars that may persist for billions of years after the merger completes. These tidal features will gradually fade as the ejected stars disperse throughout the local group, but they will remain detectable for cosmologically significant periods. Similar tidal structures observed around elliptical galaxies throughout the universe provide evidence that major mergers represent a common evolutionary pathway for massive galaxy formation. The local group's smaller satellite galaxies, the Large and Small Magellanic Clouds, the Triangulum Galaxy, and dozens of dwarf systems will experience dramatic environmental changes as the two giant spirals merge. Some satellites may be tidally disrupted by the enhanced gravitational field of the merged system, while others might be accreted during the collision process. The few satellites that survive will orbit a galaxy fundamentally different from their current hosts, with altered tidal fields and interaction rates. Globular cluster systems from both galaxies will be mixed together during the merger, creating a combined population that reflects the star formation histories of both progenitor systems. The total globular cluster count in the merged galaxy may exceed 500, making it one of the richest cluster systems in the local universe. The spatial distribution and kinematics of these clusters will preserve fossil evidence of the merger process for billions of years after the collision completes. The merger will significantly affect the chemical evolution of the combined system by mixing stellar populations with different metallicity distributions and abundance patterns. Gas flows driven by the collision will redistribute heavy elements throughout the merged galaxy, potentially erasing some of the radial abundance gradients that characterize present-day spiral systems. The enhanced star formation during the merger will also accelerate chemical enrichment by rapidly converting gas into stars and processing material through stellar nucleosynthesis. Planetary systems throughout both galaxies will experience gravitational perturbations as their host stars are scattered into new orbital configurations. Most planetary systems will survive the merger process intact, as the gravitational influence of stellar encounters typically remains too weak to disrupt tightly bound planetary orbits. However, some planetary systems may be ejected from their host galaxies entirely, becoming isolated wanderers in the expanded local group environment. The solar system's fate during the merger remains difficult to predict, precisely due to the chaotic nature of gravitational scattering processes. Current simulations suggest approximately equal probabilities for the solar system to end up in the inner regions of the merged galaxy, in the outer halo, or ejected entirely from the system. If ejected, the solar system would become an isolated island of planets orbiting the Sun through the vast emptiness of intergalactic space, far from any stellar neighbours. By the time the merger occurs, the Sun will have evolved significantly from its current state. Approximately 4.5 billion years from now, the Sun will be nearing the end of its main sequence lifetime and beginning the transition toward becoming a red giant star. The collision will thus coincide roughly with dramatic changes in the solar system due to stellar evolution, creating a period of simultaneous galactic and stellar transformation. The Andromeda-Milky Way merger represents part of a larger pattern of structure formation and evolution in the local universe. The local group itself will eventually merge with the neighbouring galaxy groups and clusters as the cosmic expansion continues and gravitational attraction draws together increasingly large structures. The Virgo cluster, located approximately 50 million light-years away, may eventually capture the merged Milky galaxy through long-range gravitational interactions operating over tens of billions of years. Observational evidence for the impending collision comes primarily from measurements of Andromeda's proper motion across the sky, using the Hubble Space Telescope and other high-precision astrometric instruments. These observations reveal that Andromeda approaches almost directly toward the Milky Way with minimal transverse velocity, confirming theoretical predictions based on cosmological simulations of local group dynamics. The collision represents the inevitable result of gravitational attraction between the two most massive members of a gravitationally bound galaxy group. Similar galaxy mergers occur throughout the observable universe, with major mergers being particularly common at higher redshifts when galaxies were more closely spaced and interaction rates were higher. The Milky Way-Andromeda collision thus provides a local example of processes that have shaped galaxy evolution throughout cosmic history. Observations of merging galaxy pairs at various stages of interaction offer previews of the events that await the local group in the distant future. Only took 4.5 billion years of gravitational attraction to bring two spiral galaxies to the threshold of merger. Only required the patient operation of cosmic dynamics to orchestrate one of the universe's most spectacular transformations. Only needed gravity's inexorable pull to ensure that the Milky Way and Andromeda would eventually abandon their separate evolutionary paths and combine into something unprecedented. The future collision approaches with astronomical certainty. Two galaxies dancing toward a cosmic wedding that will reshape the local group and create new stellar architectures from the combined heritage of spiral arms and ancient stellar populations, in the vast sweep of cosmic time, stretching far beyond the collision with Andromeda and into futures so distant that they challenge human comprehension. The Milky Way approaches its final, inevitable rest. Trillions of years from now, when the universe has expanded beyond recognition and the cosmic microwave background has redshifted into complete invisibility, the galaxy will enter its twilight epoch, a period of gradual decline as stellar formation ceases. Existing stars exhaust their nuclear fuel, and entropy finally claims victory over the organized structures that once defined galactic architecture. This ultimate fate represents not catastrophic destruction, but rather the patient unwinding of cosmic order, as thermodynamic equilibrium slowly asserts itself across scales that encompass entire galactic systems. The first stage of galactic death begins with the exhaustion of star-forming material as the galaxy consumes its final reserves of hydrogen and helium gas. Current estimates suggest that star formation within the Milky Way will decline exponentially over the next 10 to 100 billion years, with the timescale determined by the efficiency of gas recycling through stellar winds, planetary nebulae, and supernova explosions. As massive stars complete their brief lives and return processed material to the interstellar medium, the overall metallicity of the remaining gas will increase to levels that may eventually suppress further stellar birth entirely. Without fresh supplies of primordial gas from the intergalactic medium, which will become increasingly dilute as cosmic expansion continues, the galaxy will gradually convert its remaining gas reservoirs into stars through increasingly inefficient processes. The final generation of stars to form will likely be low-mass red dwarfs, with lifetimes measured in trillions of years, stellar remnants of an epoch when the universe still possessed sufficient density and organization to support nuclear fusion. These ultimate stellar children will burn their hydrogen fuel with miserly efficiency, providing faint illumination long after all other stellar populations have faded into darkness. The era of stellar death will unfold with systematic precision as different stellar populations exhaust their nuclear fuel supplies according to their masses and evolutionary timescales. Massive stars, which burn brightest and briefest, will disappear first through supernova explosions that leave behind neutron stars and black holes. Intermediate mass stars will swell into red giants before ejecting their outer layers as planetary nebulae, leaving white dwarf remnants that will cool slowly over cosmic ages. The lowest mass stars will persist longest, gradually dimming as they convert their entire hydrogen supply into helium over timescales that exceed the current age of the universe by factors of hundreds. As stellar populations age and die, the galaxy's luminosity will decline exponentially, with the characteristic timescale determined by the main sequence lifetimes of progressively lower mass stars. Approximately 1 trillion years from now, the galaxy will be dominated by white dwarf stars, neutron stars, and stellar mass black holes, with only the lowest mass red dwarfs continuing to burn hydrogen through nuclear fusion. The total luminosity will have decreased by factors of millions compared to present values, creating a dim, reddish glow that barely illuminates the cold interstellar medium. Brown dwarfs, substellar objects that never achieve the mass necessary to sustain hydrogen fusion, will constitute an increasingly important component of the galaxy's mass budget as stellar evolution removes higher mass objects from the active population. These failed stars, currently difficult to detect due to their intrinsic faintness, will become relatively more prominent as they outlast their more massive stellar siblings. Brown dwarfs will continue cooling for trillions of years, gradually fading from dull red objects to completely dark remnants that emit only in the far infrared. White dwarf stars, the evolutionary endpoints of solar-type stars, will dominate the galaxy's visible light output during the intermediate phases of galactic death. These compact objects, initially heated to temperatures exceeding 100,000 Kelvin by the final stages of stellar evolution, will cool slowly through radiative losses over timescales of hundreds of billions of years. The cooling sequence of white dwarfs provides a cosmic chronometer that will eventually record the thermal history of stellar death throughout the galaxy. The final stellar remnants will gradually succumb to various exotic physical processes operating on timescales vastly longer than current stellar evolution theories typically consider. Proton decay, if it occurs as predicted by some theories of particle physics, will eventually dissolve even the most stable atomic nuclei over timescales of approximately 10 to the 34th years. This ultimate atomic dissolution will affect white dwarf stars, neutron stars, and any remaining planetary material, converting the final stellar remnants into diffuse clouds of leptons and photons. Even without proton decay, quantum tunneling effects will allow white dwarf stars to undergo fusion reactions at their surfaces despite their low temperatures, gradually converting their carbon and oxygen cores into iron through processes that operate over timescales of 10 to the 1,000 years. These quantum mechanical effects, negligible on timescales relevant to current stellar evolution, become dominant processes in the extreme future when thermal fusion has long since ceased throughout the galaxy. Black holes will persist longest among all stellar remnants, gradually evaporating through Hawking radiation over timescales that increase proportionally to the cube of their masses. Stellar mass black holes will require approximately 10 to the 67th years to evaporate completely, while more massive black holes formed through stellar mergers or other processes will persist even longer. The final black hole evaporations will mark the end of all gravitationally bound structure within the galaxy, leaving behind only a diffuse gas of elementary particles in thermal equilibrium. Planetary systems will gradually decay through gravitational radiation losses and tidal interactions, with orbital energy dissipating over timescales determined by the masses and separations of the component objects. Close binary systems will spiral together more rapidly, while widely separated systems may persist for cosmic ages before finally coalescing. The eventual fate of all planetary material involves either accretion onto stellar remnants, ejection from stellar systems through gravitational interactions, or sublimation through proton decay processes. The galaxy's dark matter halo will remain largely unaffected by these stellar evolution processes, continuing to provide gravitational structure long after all ordinary matter has been processed through stellar nucleosynthesis or dispersed through various physical mechanisms. However, dark matter particles may also be subject to decay processes operating on extremely long timescales, eventually dissolving the gravitational scaffolding that currently defines galactic architecture. The timescales for dark matter decay remain highly speculative and depend on the unknown nature of dark matter particles. During the galaxy's final epochs, gravitational interactions between stellar remnants will gradually heat the system and cause the most energetic objects to escape entirely, leaving behind an increasingly tightly bound core of the least energetic remnants. This process of evaporation through two-body relaxation will slowly dissolve the galaxy's gravitational binding, dispersing its constituent objects throughout the expanded local group or beyond. The timescale for complete galactic dissolution through this process exceeds 10 to the 19th years. Vacuum decay, if it occurs, represents the ultimate threat to all organized structure in the universe, including galactic systems. Theories of quantum field theory allow for the possibility that the vacuum state of space itself may be metastable, subject to decay into a lower energy configuration through bubble nucleation processes. Such vacuum decay would propagate at the speed of light, destroying all matter and energy within the expanding bubble and effectively ending physics as we understand it. The heat death of the universe, the state of maximum entropy, where all energy has been degraded to uniform temperature and no further work can be extracted from any physical system, represents the final equilibrium toward which all galactic evolution ultimately tends. In this state, the expanded universe will contain only a dilute gas of elementary particles and photons at temperatures approaching absolute zero, with no remaining gradients in temperature, density, or gravitational potential to drive further physical processes. Despite these ultimate limitations imposed by thermodynamics and quantum mechanics, the galaxy's long future contains epochs of unimaginable duration, during which complex processes may continue operating. The lifetime of the longest-lived red dwarf stars exceeds the current age of the universe by factors of thousands, providing extended periods during which stellar energy sources could potentially support organized systems. Even the cooling phases of white dwarf stars and neutron stars offer billions of years during which temperature gradients might drive exotic forms of structure formation. Only took the universe 14 billion years to create the organized structure we observe today. Only required the concentration of matter and energy over cosmic time to build galaxies, stars, and the complex chemistry necessary for life. Only needed thermodynamic disequilibrium to provide the energy gradients that drive all physical processes from stellar fusion to biological metabolism. The Milky Way's ultimate fate reflects the universe's journey toward maximum entropy, a destination that remains trillions of years in the future, ensuring vast expanses of time during which stellar fires will continue burning, planets will continue orbiting, and the galaxy will maintain its role as an island of organized complexity in the expanding cosmic ocean. The final rest approaches with the patience of geological ages, the galaxy slowly winding down like a cosmic clock whose mainspring gradually loses tension in those distant epochs, when the last red dwarf stars flicker and fade, when the final planetary orbits decay, when even black holes evaporate into the quantum foam of empty space. The Milky Way will achieve the perfect equilibrium that entropy demands. Its long journey from primordial chaos through organized complexity finally complete, leaving behind only the fading memory of spiral arms written in the distribution of dark matter and the lingering echoes of gravitational waves from the universe's last collapsing structures.